Okay, so we have 1 minute. So let me say that thank you very much for joining this online meeting. It started almost 2-3 months ago. We have another online forum with a smaller number of people. And then we think that there are a number of things that we want to discuss more, so we organized today's meeting. And it turns out that we have quite a number of participants, and I think that there's something interesting that we could share. And this is a very international group, and it actually began with my meeting Professor Takahashi, because I knew that he was very intelligent in studying lightning by using satellites. That's how I heard about lightning. I mean, interestingly enough. So last time I met him again at a meeting in Taiwan. That remind me of the topic lightning. So I asked him, and then he said yes. Why don't we do it? So I sent out the letter to a number of more people. And so end up today's as you know, I'm here just to learn more about what lightning research is, and I think you agree with me. It's a very interesting and wide range field, and not just for space observation for other planets on Earth. There's a huge amount of work on lightning study. It has a lot of applications also. So today we will have the experts to talk about various aspects. And it was first begin with Professor Ivana. Professor Ivana, are you ready?
Yes, I am.
Yeah. Then Monkey, can you take off this slide and let Ivana to put on her video? Okay, please.
So can you see my screen?
Yes, very well.
Okay, so let me introduce myself. I am Ivana Kolmasova from the Institute of Atmospheric Physics in Prague. I have also a part-time appointment with the Charles University, the Faculty of Mathematics and Physics. I am mainly focusing on lightning on the Earth, the processes which are occurring inside thunderclouds. And for our instrumentation we are developing at the institute, I am serving as a product and assurance manager. So today I would like to show you some comparative study which we have done using the data from Juno spacecraft, which is orbiting Jupiter. And we used also our ground-based measurement of lightning-related signals in broad frequency range to guess what might be happening on Jupiter. So now, yeah. So probably in this group, I do not need to mention that the first evidence of lightning on Jupiter was made by Voyager when it detected these signals with falling frequency, and they are called whistlers, and there were no other explanation based on the similarity of the same signals or similar signals with falling frequency in time detected on the ground that they might be originate in lightning in the Jovian atmosphere. So it was the first evidence of lightning outside our solar system. The lightning was shortly after this radio evidence also seen by the camera on Voyager 1, and then by many missions which were flying by or orbiting Jupiter. And all these detections are shown here in the map by individual symbols. So we had optical measurements by Voyager 1 and Voyager 2. We have measurements by Cassini, by New Horizon, of course, Galileo. And all of these optical measurements were with only a few few detections around the equator. All of them were mainly done in the mid latitude or high latitude. And so before Juno, we have nearly 500 optical detections and 167 Whistlers, which these signals are so dispersed. It means that the lower frequency arrived so far after the higher frequencies, because the signal was penetrating through the dense plasma iotorus, and then it accumulates this dispersion. Juno mission arrived to Jupiter in 2016, and it was the first mission which was able to see Jupiter from very low distance, because close to the perigeo it was at the distance up to 1.1 Jovian radii. The main goal of Juno mission, of course, is not lightning. It's to understand the origin of Jupiter, and there are instruments which map gravitational and magnetic fields in very high resolution. So we have new magnetic field models, new information about the gravity of Jupiter, and variations of the composition of deep atmosphere used to the microwave instrument. And there is also an instrument which explores the magnetosphere and aurora. As I said, Juno was able to come very close to the Jovian surface, and it's very appropriate for detecting of Jovian lightning. After the prime mission, the orbit somewhat changed, and now it is focusing on the Jovian moons. And unfortunately, it seems that Juno mission will be stopped this month. I still strongly hope it will not happen, but I was talking to several planetary scientists last week in Washington, and it seems that it is true. So yeah, it's I think it's very pity, because the instrumentation is in good shape and could bring us new information still after the prime and extended mission. So we will see. There are several papers which were describing lightning on Jupiter detected by Juno. They are mainly in the electromagnetic range, but I'm here showing as the first one also the lightning detected in optical range by the Stellar Reference Unit, and which was able to detect with lightning in optically with much higher resolution than all previous mission. I will show the resolutions later. So I will be focusing in my talk mainly on this last paper we published in 23 in Nature Communications, mainly that lightning in Jupiter pulsates with similar rhythm as in-cloud lightning on the Earth. So these are electromagnetic signatures of lightning, which were detected by Juno at different frequency ranges. We have a low frequency receiver measuring from 50 Hertz up to 20 kilohertz. This map shows the projection along the magnetic field line of every position of Juno when it detects one Whistler. Here is the time frequency spectrogram showing these Whistlers. We call them rapid Whistlers because the dispersion is here around few milliseconds, which is like 1,000 times faster than was detected by Voyager, and it's because the plasma through which the signal propagates is not dense ionough to accumulate these huge dispersions. So we even think that there might be holes in the Jovian ionosphere, because such a very low dispersion cannot be otherwise achieved. Then we have lightning detection in the high frequency range from 20 kilohertz to 150 kilohertz. This is the upper part of the low frequency receiver. every detection projected a straight line to the map is on the left bottom plot. We call them Jupiter dispersed pulses, and here is the time frequency spectrogram showing it. Such type of signals was not detected on Jupiter up to now. Juno was the first one, and the same with microwave detection. So microwave instrument detected lightning-related signals in 2 frequency ranges, 600 megahertz and 1.2 gigahertz, and each signal again projected as a straight line. A projection of Juno to the surface of Jupiter is here represented by blue and red circles. Here, this histogram on the left is a very new one. I finished this summer the whole prime mission search for lightning. And it's still very similar to what we saw before. It means that lightning is really concentrated in mid latitudes and a little bit to higher latitudes. And it's the explanation is which we can offer for this distribution is quite simple. It means that the thunder clouds on Jupiter are not made due to heat from the sun, but due to internal heat from Jupiter, and which is going out, namely in mid latitudes, and also the abundance of ammonium in the equatorial region might play a role in the absence of lightning on Jupiter in the equatorial region. Here are the time resolution of Jovian lightning processes in optical. The cameras on Voyager, they have exposure time and many seconds on Galileo as well. It means that they have detected flashes or even groups of flashes. In electromagnetic recordings, it was better, of course, because there were individual lightning whistles, and each individual lightning whistle corresponds to one individual lightning strokes, and the minimum inter-whistle interval which was found was 1 second. With Juno became the resolution much better. In optical range, the stellar reference unit was able to see the interflash separation of tens of milliseconds, and in electromagnetic records it's even better. The microwave instrument has unfortunately 100 millisecond integration interval, so they always collect different lightning phenomena. They cannot distinguish what is if there is an initiation phase or something like return stroke or more of them. But in case of radio receivers, we have the minimum interval about 3 milliseconds. In the high frequency part of the low frequency receivers, we have even available to distinguish the pulses which are 250 microseconds apart. So this is a nice resolution which we use in this study. So this is the radio plasma wave experiment named WAVES. We are using the low frequency part of the receiver, which has two parts. The low part relies on data from 2 antennas, a search coil, which is very small, like this size. Where is my camera? Yeah, this size only. And then the electric dipole, which has a V shape. And what I found very nice, that even if these antennas are very short and the search coil is very close to the spacecraft, it's electromagnetically quite clean, which is not the case we have on the other spacecraft, as for example Solar Orbiter or JUICE, which is now on his way to Jupiter and its icy moons. So here are the groups of lightning-related signals which we found in the recordings of the low-frequency receiver, this high-frequency part. So these are multiple Jupiter dispersed pulses. You can see here the number with Masafumi Imai, which was not able to join us today because he's presenting Czechia in Osaka in the on the exhibition. So we went through nearly 500,000 snapshots to find the 2,000 intervals in 3,000 snapshots with multiple Jovian dispersed pulses. You can see that they are quite regular, surprisingly. So we were wondering what these groups of signal are, and we found similar groups, of course, with worse resolution in the VLF part of the receiver, but still there were numerous whistlers, sometimes with quite regular interpass intervals. You can see also that all these signals are cut from above, but it's related to the propagation through the plasma in the equatorial region, where there is this cutoff frequency is due to propagation. So here we found snapshots with at least one whistler at 4,000, but number of snapshots with more whistlers were only 120. And we have from this data set 353 interpass intervals, which we plot all the detections here. And it is not surprising that they are simply accumulated again in the same areas. It means in both hemispheres on the middle and high latitudes, the blue circles are multiple whistlers, and the black circles are multiple Jovian dispersed pulses. They were, in case of whistlers, they were found only very close to the planet. And in the case of Jovian dispersed pulses, the groups, they were found up to 300,000 kilometers from the 1 bar level. So here are two histograms showing the results. There are number of whistlers within a snapshot. This of course is limited by the length of the snapshot, because unfortunately, in case of such mission, we cannot have too much data, so they were snapshots taken only once per second, and they are quite short, so the numbers in this histogram are limited by the length of the snapshot. But here is the median interpulse intervals for both data sets. It means in black for Jovian dispersed pulses, in blue for whistler intervals, and we can see that the median interpulse intervals was about 1.2 milliseconds. So we were wondering what these groups of pulses might represent and look at their terrestrial counterparts. So what are the groups of signals in which we can see in terrestrial recordings? So we can have groups of lightning flashes, but we are quite far apart. Here we have about like 10 to 20 milliseconds apart. We can have initial breakdown pulses in inverted IC flashes. This is this spectrogram, where the pulses, here is the waveform of that spectrogram, which I load down from our 90 megahertz broadband measurements. This is from Czechia, from the Milešovka mountain, to show what the receiver on Jupiter might see in the spectrograms. And this lower one are initial breakdown pulses in like normal IC flashes, and this starts to be quite similar to what we see on Jupiter. It means the pulses are about 1 millisecond apart and not completely regular. So to summarize, we think that on comparison of the interpulse intervals with characteristics of what we see on the Earth, we hypothesize that if lightning discharges at Jupiter propagate in water clouds at similar velocity, 10 to 5 to 10 to 6 meters per second as in terrestrial lightning leaders, then these groups of pulses might be evidence of extension of lightning channel in the stepping manner. And these steps might be like 5 to 10 times longer than steps observed during the initial breakdown of terrestrial lightning. But it's not probable that these multiple jovial events are similar to terrestrial multi-stroke flashes. So we think that we probably saw the step-like extension of jovial lightning channels. Thank you.
So questions? Okay, we have a question from Yof. Yeah, please.
Hi, Ivana. Thank you for a great talk. Can you estimate how large, in terms of spatial dimension, would be such a Jovian stroke in the water cloud? I mean, how big or extensive in terms of kilometers?
It's very tricky to do because there are many assumptions. So I think that with the velocity, I relied a little bit on your old paper, the velocity of the leader propagation, because you try to, I think, estimate the fields there. So then maybe the velocity might be similar, but as we saw such a small part of the development, I am really I'm scared to guess how the lightning could be long, but I would guess that the factor of 10 in comparison with terrestrial ones, if I see the steps, which might be 10 times longer. So then if the whole thing is 10 times longer, but it's terrible hand waving.
Thank you.
Okay. Yes, there's another question. Professor Liu.
Oh, yes. I noticed that the microwave radiometer is used. I wonder what...
Can I hear you?
Okay, can you hear me now?
Yeah.
It's better.
Can you hear me? Okay. Oh, my question is about the use of microwave radiometer. What is it used to monitor, and what is the mechanism behind to support the measure? Thank you.
You mean the microwave radiometer measurement?
Yes.
It is quite tricky because they rely on 100 milliseconds accumulation of the signal and looking for some peaks in the temperature. So they describe it in the paper in the detail. I'm not really I cannot explain it really properly. But what I know that these are short pulses for which they do not have other explanation that they came from lightning. The distribution of lightning is similar to what we see with the radio measurement, and we also have like several, I think, a few tens of the detections which could be the same if we, of course, take into account their resolution. So this is simply the peak in the temperature, which is measured by the microwave instrument.
Okay, thank you. I think that we have to hurry on to the next talk. The next talk will be given by Professor Shri Gopalakrishnan.
Good morning, sir. Good morning, everyone. So I will be in this. I'm very much glad to give a talk in this webinar. So I will be talking about the Indian Lightning Direction Network, and then also that one of the important applications that's called Damini mobile app. So I will be giving a small overview about this one. So I am working in Indian Institute of Tropical Meteorology, which is only the means one of the premier institute of atmospheric research in India, and even in the Asia also well known atmospheric research. So you can get the details about our institute in this link. So we have means in our institute we have carried out the mostly that means that research on the monsoon prediction, monsoon forecast, short range forecast, and then also the short range, medium range forecast we are having. And then now recently we have added that means that Bharat forecast, which has been that we can give that means the forecast to that something around the 6 kilometer range. So that much accurate forecast we have been developing. Along with that, we are also having a division for that means the air quality research, as well as for that means the thunderstorm, and then also that the lightning research. So coming to that our division. So we are not only doing that only for the lightning. We are having our one means that we have started our institute for about the last 30 years. We are having an atmospheric electricity observatory. We are having that very much suite of instruments which can be that can be used for atmospheric electricity measurements. So all this instrument has been fabricated in our institute by us only in our institute workshop, and then we are using it for that long time. We have also conducted many of that means the campaign mode observation over the sea, over Arctic, over Antarctic, nearly everything. So, and then in that, one of the special thing we have in our institute is called that means the vertical field mill, where we can suspend the drop, means that vertical some of the electrical drops, and then see the electrical interaction. So you can see that one. So how this drop is been affected by the electrical forces. So that will be very much interesting to know about that, because this thunder clouds, which is having that, which is producing the lighting, that is very much means get electrified. So what means how this electrical field is just affecting these water drops, or even the cloud drop within the thunder cloud, is one of that means that very much not so much understood. So we are having in our laboratory, we are doing that, producing the simulation experiment. So you can see that how this water drop is being distorted, and then that breaking up, and then so we are now studying that collisions, interaction, and then that water drop breakup. Everything we are seeing by applying that electrical field within this means what you call the small wind tunnel. So we are producing the wind, as well as we just want to just that we are just means you can see that water drop is been that suspended between by applying that electrical field, and then we study that lot of that means that the distortion patterns of this water drop. It is that one of the important theories we have seen this one. So we have seen that horizontal electrical field decrease the collision efficiency of the colliding water, and then this electrical field significantly modified the drop size distribution within the thunderclouds. And then this is the important the recent results we got from this one. So it is now published in the GRL May 2024. And then now that coming to the lighting. So why our institute has taken, though our institute is mainly focused on that means the weather forecast and atmospheric means the monsoon research. Why we have taken taken up this study is over the India we have seen that lighting death, especially that lighting death is increasing continuously over the years. And then you see this graph over this in my right hand. So over the recent years, now that only that lighting is taken that much of the toll. That earlier we have that means that loss due to the cyclone and other things. Now the cyclone has come down to Tensei, even that means that death due to that cyclone has come down to just about that less than about 100. Whereas this only the lighting is increasing, something around 2,000 to 2,000 people are dying every year. So which is so much disturbing. So we are so that's our institute has taken up this study. And then so earlier we are not having any kind of means the lighting observation. So we are just dependent on only that only some satellite data. now we have to we are now having that observation only. So if you see that even over that I told you that lighting that is always especially in this region, so northeast, and then this region, eastern region, and then this part central region is very much higher. So that's why, and then we have seen, and then if you see that lighting climatology, and then even the trend, and then each time we are having a trend is increasing during every year. So you can see that even that every season, this season is called the March, April, May, which we call that the pre-monsoon season. So here you see that lighting trend is increasing, and then here also during that monsoon and June, July, August also lighting trend is increasing, except for during that winter period. Every time we are having so much increase. So no, so this slide you can see that one. So you see that lighting, and then so our study released that means the lighting has increased by about something around the 33% over the monsoon, and then some that overall increase is sometime more than about the 30% increase in 1996 to 2013. So this is very much alarming. So that's why we have now stated that the Indian Lighting Network. So how this network is working on the principle of the time of variable technique. So that each sensor, so we are having at least that 4 sensor we have kept it, so that each sensor will receive the pulse from the different thing depending on the distance from the pulse, and then these distances are some represented by the this red graph. And then we are now processing that by having some kind of this one. So we are having this one. So once we find out that that difference in time where they are just overlap is the place where that lighting has really happened. So within this network, so we have started. So we are using that LLL network. This is this is from that means the commercially available. It is brought from that the Earth networks of the USA, and then so this network. So we are having this kind of antenna, and then this is being this kind of the lighting sensor we have. So with this one, we are using the 2 bands. Below some about the 1 kilohertz long range direction. 1 kilohertz to 1 microhertz has been used for that locating the return strokes as well as that cloud to ground rays, and then also 1 megahertz to 12 megahertz is being used for the used to direct that means that's IC lighting. So all this lighting is being directed. All the lighting which has been directed by S1, S2 or the different locations that has been received from that means the lighting receiver, that is from comes that lighting receiver, then it goes to the processor, post processor, and then we are giving that then afterwards we are getting that the live feed of the lighting where that lighting is exactly existing. So that final product we are taking this one wherever the flash is happening within about the 700 milliseconds within the 10 kilometer merge into the single or that multiple flash as only the single place. So our lighting network gives about that means the exact time, latitude, longitude, type of the lighting, whether it is the CG or even that IC lighting, polarity, positive or polarity, as well as the peak current. So these are the product we are getting from our lighting network. So this light node, and then he's having that. So we are kept that though they are telling that baseline distance can be around the 200 kilometer, we have kept the baseline distance as far as possible less than 200 kilometer, something around that 150 to 100 to 100 to 150 kilometer. So now in our lighting network we have now that 112 sensors are there. So even that proposed sensor has been also been established except for that bottom region. So other places it is there. Now we are having that 112 sensors, 110 sensors have been in our network. And then with this network, we can get the lighting location, something around the average of location accuracy is around the 300 meter. Direction efficiency is about that 90% for that CG lighting, and IC lighting is only 50%. Okay, so this lighting network, so we have see how and then this way our screen is involved. So whenever we are getting that we are just monitoring that lighting happening all over the India. So this type of thing, our screen is involved. We can get that. So this color. Wherever that means that we can see that live lighting where it is happening and how is it that progressing also. So this way how it is progressing. Also, we can get this. So by this, having the progression, we can get the convective weather. Also, we are getting it. So and then this way we are getting all these things. We can also get the dangerous thunderstorm alerts also from our lightning network. So this lightning network is having, and then we are now having some that's very much confident about the lightning network, because we have already validated it. So if you see that one, so the validation is done by using that even that satellite measurement, satellite pictures. Also, we have seen where that particular convective cloud is there, whether that lightning is happening ever. And then we are also having so much big, I mean, within our India, we have having that very much good radar network. So by having that radar also, we have seen whether means that the overlapping the lightning product along with that means the radar pictures, that also we have seen. So that also we have seen. So we must, and then also as I told you, we are using that field mill also. So we have use our own field mill for that validation. So we have used that field mill, we have used that electric means that radar product, we have used the satellite product, and then see whether that particular lighting is really happening, means that kind of thing. And then we are also sometimes we are getting that user feedback also. So that user feedback also we are getting that. So all these things have been used for that for our validation of this of our network. So now this network is that fully validated. So our paper was published in Atmospheric Research recently, 2025. We have published that. So in that paper, you can see that one means that Vishwakarma et al. You can find that how our network is been established. And then so within our network, so one of the two things I want to show you, some peculiar things we have recently got from our network. So we have seen that during that here, that is one of the things is that high occurrence of the positive CG lighting with that higher current amplitude. So you can see that positive CG lighting, how it is increasing, especially during that only that June, July, August month. That is only that where we have that monsoon season. So this monsoon season, that is one of the important thing, because that monsoon season, people go over, agricultural people also only going, that is only the sowing time. Agricultural farmers will be just working in the field. That time, it is that time only we have seen that there is a rise in that, means a positive CG lighting. As all you know that this positive CG lighting carries a very high peak current compared to the negative field lighting. So at that time, so nowadays we are getting that, that's why we are getting so much lightning fatality even during that monsoon time. Because that we know that pre-monsoon time, it will just means the thunderstorm will occur, and the thunderstorm will have lot of lighting, and then people also are being installed. But during this monsoon period, though we cannot mean that is only that the main sowing time for the farmers, agriculturists. So these people, they go out for that agricultural production, agricultural work. So at that time, so this kind of this thing means that when we are seeing that this rise in that CG lighting, that also with that high peak current, so that is a worrisome thing. So that we have found that recently. And then one more thing, that's why you have to avoid this worry, means that there is a sharp increase in the peak mean current during the summer monsoon. So, but why we don't know, but we are now studying it. You can see this one. So this figure very well explains that the peak current is increasing, especially over that during that monsoon months. So that's the only thing. So this is also that increasing current essentially. And then one of the peak things we are seeing that what we are saying is only that lightning jump. So during this particular time, you can see that an afternoon time is very much so the flash becomes just double in the just 10 minutes, and then that then only that thunderstorm disappears. So this is also one of the important things. These are the two main results I want to show you that one. And then I told you about that only that Damini app. So we have now observing the lighting, but we have to, as I told you, that we have to give that information, because there is no information about the lighting, where it is happening, or how it is happening, and everything. So we have to, I told you that a lot of people are also dying. So we have to somehow give some kind of information about the lighting happenings. So that's why what we are doing is we have now developed a mobile application that is called the Damini Lightning Alert Mobile application. So this application will give you something whether the particular state, wherever using the GPS as well as the phone GPS. So we are just disseminating our thing. So we have to give around that within that 20-kilometer range whether some particular lighting is there or not. So this kind of app is being that you have means widely used. Now even our government is also advising the people to use this particular app, because in this app we are giving that whether the particular over the region within the 20-kilometer region whether that lighting is there or not. So we can see that whether it is not, there is no lighting. When there is a yellow color appears, the possibility of lighting, and then when there is red color is the that lighting is happening within your 20-kilometer area. So there you are in a danger zone. You have to go out immediately. So that kind of a thing we are now doing it. So all these things are now helping that not I am not telling that it will just bringing down the fatality rate, but at least the people are getting. But earlier there was no lighting warning or about that one. So our thing is now our people are now using it. Our even our government means even our government is also advising the people to use this kind of a lighting app to know about that where that particular lighting is happening. And then so this app now we have developed. First initially we have developed only in English. Now this app is available. As you know that India is having a lot of languages, something around the 14-15 main languages. So all these languages we are now disseminating this information. So that is also the people are now using it. So that is a very good thing. So as I told you, now the lighting has been so our IMD also, that India Meteorological Department is now taking our own that lighting observation, and then they are everything they are putting on that along with that brighten temperature and everything they are using it. So how that particular lighting is happening, which time is moving. So there are and then also there are many kind of uses with the IMD is using it, and then that forest department using for that forest fire portal they are also using our data. So now because of this efficiency of the network, our user base now is being broadened. So and then now we are getting a very good day. So now we have about 112 this one. Now we have a proposal to have, as I told you here, something over that neighboring region, especially this Bangladesh region. We are seeing it because many of the thunderstorms is just developing over this Bangladesh region and then just affecting this kind of Eastern India. That is that Eastern India is only that means one of the hotspots for the lightning. So we are now thinking of putting some of the sensors over the Bangladesh region, so we can have a relation, and also that Nepal region, so that we can have a good observation over, especially over that eastern sea, which is having one of the important lighting hotspot zone over the India. So and with this one, I just thank you all for your careful listening. I'm just stopping over here.
Thank you very much. Yeah, it's very standard lecture. I think there are lots of things we need to understand more and learn more. Any questions to Professor Gopalakrishnan? And if you, yes, please, go ahead.
So are you saying that I can ask question now?
Yeah.
Okay. I noticed that you show the awareness about lightning research. I see that the death numbers increase very much around in year 2007 to 2019 from your slide, and before 2007 the death number remains almost it's up and down, but there's no obvious trend, increased trend. So can you explain why the death number increased very much?
Yeah.
That time frame.
Yeah, we are seeing that there is an increase in the lightning. So earlier we don't have much information about the lightning because we are just dependent only on the satellite data. Now we have a data over our own network. So that now that increase in that number of data. So that is only that helping us to find out that trend. That is the major advantage of this one.
Okay, thank you.
Any other questions? Oh, yes, please. Professor Shankar. Professor Shankar, we
Yes,
cannot hear you.
thank you. Very nice presentation. Although I have joined slightly late, could it be possible, this is comment, just could it be possible along with the network sensor, if some instrument or something should put so that any lightning happen, it will go directly to into the earth. Is it possible?
Directly to?
Into the earth.
Yeah, then only the earth only. No, that is directly it means all the lighting which is just striking will just means that the current is just going into the earth only, just into the surface only. So all this current is been that means that lighting starts from the cloud and then ends only at the surface of the surface of the earth. So all the lighting that is coming that goes to the earth only. There is no need to put any kind of instrument. So what you are telling is means that earthing instead of that getting that this one. So we are having that kind of means what you call that means that lighting protection system or that lighting arresters we are being producing. So that kind of if we having that kind of means that good lighting arrestor system, then it will directly pass on to that this kind of this lighting current to the earth. Yes.
Thank you. Thank you. That's good.
Can you hear me?
Yes, now we can hear you.
Yeah. So, sir, you mentioned that lightning current, IC lightning current, 2020 and then 2024, that is much differences in the current. So, is this current is due to the number of sensor increase? We increase the number of sensors, or so that we are estimating much higher current based on these sensors, or it is something else? What is your?
No. It is not because of the increase in that means the sensor density is not the problem. We are also observing that because that earlier also we are having the sensor density over that especially that result I have seen over only over the central India. So central India place we are not increased much sensors. So that the result of the sensor that we are getting the first time results. So earlier we don't know about the current associated with the lightning. Now we have the first time we are seeing the current associated along with the polarity also we are getting it. So we are getting that one. So this paper is published in JDR. So you can see the paper also in that one. Rakesh Ghosh.
The next talk will be given by Professor Chenglin of National Central University. His talk title is Observation of Green Emission Intensification Associated with Lightning. Professor Gu.
Yes.
Please.
Thank you for opportunity to talking about our observation.
Can you make it full screen?
Yes. It is something called. Okay. And my talking about is green emission enhancement at the gigantic jet top. Just last maybe 5 or 4 years ago, the observation found the green emission enhancement at the sky top. So now we're talking for the gigantic jet. In this case, there is no green emission enhancement. We will be show the case in the later slide. This outline is electric coupling in the middle atmosphere in Earth and the enhancement of green emission. And we using the chemistry model to discuss in this for example the green emission decay time and to compare with the model. Now it's electric couple. It's an overview for the middle atmosphere. Middle atmosphere is a high between maybe there is some different definition. It's above the sphere and to the maybe the lower boundary of the ionosphere between maybe 10 to the 100 kilometer. We call this the middle atmosphere. There is some coupling between the lower atmosphere and to the higher atmosphere. So later, the lightning will be there is some current generation or charge changes, so there will be caused steady electric fields, and will be trigger spike, and then some the lightning current will be radiating the electromagnetic wave to hitting the bottom of ionosphere. There is we call this the helps. And some current, some charge will be enhanced heating just above lightning charge here. We call this a halos. And then some lightning channel will be usually the lightning will go down to the ground, connect to the ground, but some lightning channel will be discharged into the ionosphere. We call this the small one is called a blue star, the blue jet. The bigger one will be trigger the upper size or the spike. We call this a spike. So we call this blue jet trigger the spike. We call this gigantic jet. Here we show how to observe the spikes. You just using the camera, low light level camera, and they set up to find a location. There is a good thing. There will be if we observe the southern storm cover, something will be happening here. So here this we call it a changing main event, include different kind or upper discharge events. It's one of these global electric circuit, because we have a series talking about the south will be current into the bottom of ionosphere, and will be leakage some current return the ground. So the gigantic jet is observation evidence to show this global electric circuits. But we talking about the electric dynamic between in the middle atmosphere, but some will be gas dynamic here. So there is some coupling between the lower atmosphere to the upper atmosphere. So there will be a change difference. For example, neutron density and neutron wind or something. There will be changing the middle atmosphere dynamic. This summer we have a campaign. We compile low atmosphere and middle upper the atmosphere scientists to do we call this a full atmosphere experiment in Taiwan. We focus in the south of the Taiwan. We set up a lot of instruments, including LiDAR and something, light level and the radars. And to see the southern storm the lifetime, how will be changing their environment. So that's our campaign. We have maybe all the atmosphere scientists in Taiwan will be joining this group. So we focus in the south of Taiwan. There's because this place is just there's a high plain, but just at the right side they have a very high mountain, so they will have some we call it the different land surface, then different land effect to the atmosphere. So our group support one campaign. We have a low light level camera station in different places. Here we show their observation, so they will overlap near the Taiwan. So we also have some UF station, but right now we need to repair here. And we right now we have this. We also have DC field being to along the southern coast. And we also have some lightning detection network. For government, they have CWA lightning network, and also international lightning network. For the DC field being mirror, they have because they have a charge. They have if the sun coast, they have some electric fields changing. So using this one, it's a real data. Just in August, we can early warning about maybe 40 minutes for the solar storm. I think that's a good instrument and wire usually in worldwide. And here we show the standard picture from our campaign. Here is a gigantic jet here, and spy here. Also have some errors. And here yeah, that's a gigantic jet. Yeah. The next one is very short. It's a spy here, and here is errors here. So we have one campaign near the Taiwan. So if you have the satellite, you can looking for changing where maybe we can have some coordinate observation. Next, we're talking about our topic for the green emission enhancement. Chenglin have found maybe 20 years ago from the 2002 or 2003 from the Pascal in the United States and Shri in Taiwan, Professor Shri in Taiwan. And he found a different kind of Chenglin here. Just maybe 2000, about this year, they have some green emission here taken from the photograph. And recently, there's always a lot of gigantic near the Taiwan compared to the other place in the other place. So, for example, just 2023, they have you can see it's a very bright blue jet in the gigantic here. And 2 years ago, yeah, gigantic. So we have because the front camera is always installed to monitor the security, but sometimes there will be a server gigantic jet because the gigantic the Python is and the time is in compared to the supply sometimes is a very happen in a very short time. Gigantic jet can less maybe a half a second. So sometimes if you have a camera, even you have a cell phone, you can observe a gigantic jet. And here we show we just find if the green emission is will be happen in the top of gigantic jet. But in this case, it's not very easy to find. Or in this case, we identify the green emission here. And we using we are modeling from the very microscope to the larger scale, and to calculate the collision between the molecule nitrogen molecule oxygen, and we have to do some simulation for the supply. And we using a numerical model to see how if we have a large streamer to here. So it's very difficult to simulate the full all the supply, the whole supply, because supply is consists of very streamer. The past streamer is a nonlinear electromagnetic wave to because separate charge emission electric field. Electric field will be enhanced ionization, and more electron will move, and it's a nonlinear process. So it's very difficult. Here we combine with our Shri model, and with we just focus chemical and to see for this case, the here is gigantic jet here. So you can see here's a very obvious green emission enhancement here. So we just we have we can using this the summation result to find to compare with our model. For example, the time scale. Here, I just showed we have a plasma chemical model to describe middle atmosphere chemistry, and to see green emission here. Here we set up different parameter for different material electric field to simulate electric field. We want to do something. For example, because in this case, we want to compare to our observation. It's a time. It's a radius. We want to compare to our solution. It's a two dot because this camera is just 3 frames per second, so it's a slow camera. But interesting for the gigantic jet, it's very slow, so you can catch the green emission after the gigantic jet. So we don't need to the high-speed camera, but we just use the small camera. We can easily to catch the green emission enhancement, because the green emission lifetime is just a half a second. So this model result is this model result in this our observation. So it's very close to our result, and we also find what will be some gigantic will be have a green emission enhancement, but some not. So we also compare to the current moment of the gigantic jet, and we have some calculator to estimate we get this emission intensity. How to using a theoretical model to predict this brightening enhancement. So he hit the calculation. But here I just want to mention not most of the gigantic jet will be enhancement, but we found if a gigantic jet have it's a carrier size gigantic jet. For example, it's not too much enhancement here, so they don't have enhancement of the green emission. But in our case, you can see there's a very huge. We call it a diffusion region. So this diffusion region will have a green emission enhancement. That's our result. So that's our new observation for the gigantic jet, and the gigantic jet have green emission enhancement. We found just last year gigantic jet observation. Thank you. I think I just start here. Thank you.
Okay, thank you, Professor Koo. I think it's quite interesting work and complicated things. Questions to Professor Koo? You could just raise your hand and or turn on your mic and ask. Yes, please, Yahui.
Hey, Professor Gu.
Yes.
Yeah. So thank you for your talk. It's really nice to see a beautiful lightning pictures in Taiwan. So I do remember there are a lot of lightnings in Jiayi, where you set up the the experiments in Jiayi. So I wonder if there's something to do with kind of mountain region, because that Jiayi in Taiwan is closer to the Alisa mountain.
Yes.
Yeah. Did you know, like, is that because of the mountains to trigger more like lightning observation? Yeah. Thanks.
Okay. In this campaign, we not just focus lightning, but lightning. We have found this Jiayi is have a very high frequency or lightning event, maybe first or second in Taiwan. So that's the first reason. And the second reason is for we just looking for how the thunderstorm will be initiated. The lightning is maybe the precursor for thunderstorm. So that's another reason for we want to find thunder conversion will be initialized, but maybe they have maybe a bigger event. For example, in this August, we have a very heavy rain in this region. So the thunderstorm will be very intensity within this region. So we choose this site for our campaign.
Oh yeah, okay, thanks. Yeah, I heard a lot of kind of news that people kind of complain or scared by the lightning. Yeah.
Okay. Yes.
Yeah.
Yeah.
Okay.
Sorry.
Yeah. But yeah, thank you. Okay. Thank you.
So, other questions? Thank you, Professor Ko. Yeah, thank you.
Thank you. Thank you.
And the next question, sorry, the next talk will be given by Professor Georg Fischer from the University of Graz. Professor Fischer, are you ready?
Yes, but I think I need to share the screen.
His talk is on the radio wave polarization of Saturn lightning.
So then I'm starting. Yeah, good morning, or it's better good afternoon for you from Graz. This is Georg Fischer. And my talk will be about the radio wave polarization of Saturn lightning as it was observed by Cassini. And actually this work has been published. You can see the link down here below with the same authors and with the same title. And we did this research in the frame of our common project, which is funded by the Austrian Science Fund and the Czech Science Foundation, about open questions about Saturn's radio emission. And the open question here is actually, is the polarization, does the polarization sense of Saturn lightning, the radio emissions, does it depend on the hemispherical location of the lightning storm? And this is the question I'm actually talking about. But first, let me give you a brief introduction of lightning on Saturn. Initially, they were detected by the Voyagers in 1981, and then they were termed SEDs, which stands for Saturn electrostatic discharges. And I understand them as the radio emissions of Saturn lightning, which are detected in the frequency range from a few hundred kilohertz, which is the ionospheric cutoff of Saturn's ionosphere, either up to 16 megahertz in the case of Cassini, or for the Voyagers, it was up to 40 megahertz. Cassini spacecraft was in an orbit around Saturn from 2004 to 2017. And within these 13 years, we detected more than 20 million of SEDs by the antennas and receivers of the Cassini radio and plasma wave science instrument. And even these radio emissions, their power is so strong that they're in the frequency range of a few megahertz, that they are 10,000 times more intense actually than Earth lightning. And this is why they were also detected by a ground-based radio telescope, the UTR-2 in the Ukraine, which today is unfortunately not operational because it's actually in the war zone. And these SEDs, the Saturn lightning, and that was actually first found with Cassini, they are related to bright cloud systems in Saturn's atmosphere. So you can either have, you can see at the image at the bottom, you have a cloud system with a diameter of around 2,000 kilometers, as it was imaged by Cassini, but also amateur astronomers on Earth contributed to this. But we also had the so-called, we have seen in 2010 and 2011, a so-called great white spot. And this great white spot, you can see the top image, it had a diameter of about 10,000 kilometers. And within a few months, it developed a long tail which surrounded the whole planet. And actually what you can see, also this curve here, this is the wind speed profile of Saturn, because this is important. You have, if the gradient of the wind speed is too high, then the storm gets torn apart. And that's why all these SED storms were located at specific latitudes. So in this wind speed minima or at the equator. And this is what I show you next here. This shows you the whole Saturn lightning activity during the Cassini missions. And there is a big difference between Saturn and or Jupiter and Earth. Of course, on Earth and Jupiter, you have lightning there all the time, but that's not the case for Saturn. So you have long-lasting SED storms, which last weeks to several months, but you also have long periods of no lightning activity. And in fact, for example, we had a large gap in 2006, 2007, and we had actually no more SEDs after November 2013. Also, the mission lasted until September 2017, when Cassini burned up in Saturn's atmosphere. So for almost 3 years, there was no lightning, although the instrument was on and we could have detected it. So as mentioned before, the storms are only detected at specific latitudes. So 35, we detected them at 35 south at the equator, 35 north, and 50 north. So either they are at this wind speed minima or at the equator. So, and this is, the next slide shows you a typical data product of Cassini APWS, a so-called dynamic spectrum, which displays the intensity of the lightning as a function of time, here over 7 hours, and frequency. It goes from a few hundred kilohertz to 16 megahertz. And these vertical streaks, you can see on top, they are the SEDs. And you can see one full episode, which means Saturn is rotating quite fast, 10.5 hours is the rotation period. And you detect the lightning when the storm is on the side facing the spacecraft, and you don't detect it when it's on the other side. Also from the images, we know where are the clouds. So, and using this, actually, we found that there are also so-called over-horizon SEDs. Because what you can do, what you see is also you have this low-frequency cutoff. And using this low-frequency cutoff, you can actually determine the peak electron density of Saturn's ionosphere, because the storm is in the atmosphere, the radio waves have to pass the ionosphere, and the spacecraft is outside of the ionosphere. So, and some SEDs were detected when the storm is still beyond the visible horizon. This is a radio wave propagation effect, which we call over-horizon SEDs. And like before, where I've shown you the intensity, and one thing I wanted to mention is normally it's a broadband emission, but you only have these short vertical streaks actually because the receiver is sweeping frequency. So you can make this dynamic spectrum intensity as a function of time and frequency, but you can also show not just the flux density, but also the circular polarization, the total polarization, and the linear polarization as a function of time and frequency. You can show these polarization spectra. So here it's a spectrum over 2 hours. The frequency is linear up to around 2 megahertz. Here, Cassini was at 70 degrees south. And actually what you can see is actually that when you focus on this, on the upper right panel, you can see we have this SKR, this Saturn kilometric radiation at a few hundred kilohertz. This is the radio emission from the aurora, which is red here, which means it's left-handed polarized. The Stokes parameter V is +1, whereas the SEDs, at higher frequencies, you can see they are blue, which means they are right-handed polarized. So what you also can see is actually that we have some spacecraft rotation also. And in the beginning, for example, this angle beta, that's the angle between the antenna plane and the incoming radio wave direction. And this is, if this is too small, the polarization determination and the intensity determination doesn't work, which are shown, and then that's why you can see the spacecraft rotation also in this spectra, because this is how you measure this SAD polarization. I have to say we have a fully calibrated antenna system of 3 monopole antennas, which also has a dipole. And basically what you solve is this linear equation system, which is an equation of 4. These are 4 equations with 4 unknowns. Your unknowns are the S, the intensity of the lightning, which you want to know, and you also want to know the Stokes parameters. QU describing linear polarization, the Stokes parameter V describing the circular polarization. You have of course, for measuring polarization, you need at least 2 antennas. So these 2 antennas give you 4 measurement values. You have the autocorrelations of each antennas, and you have the real and imaginary part of the cross correlation. And these are these products of V, as you can see. We also have the effective length vectors, which we know because the system is fully calibrated. And then actually this matrix M actually just represents the geometry between the source and the antenna. So basically what is important is the so-called antenna plane. And when the angle between the incoming radio wave direction and the antenna plane is smaller than 20 degrees, then this equation system is ill-conditioned, and then you cannot properly determine the polarization. So basically we have to say this angle beta has to be greater than 20 degrees, then you can properly determine the polarization. So now let's do this. We did this polarization determination here, and here what is shown is the degree of circular polarization on the x-axis from -1 to +1, and the degree of linear polarization on the y-axis. So this semicircle is actually represents a fully polarized wave. As you can see, actually, for this, and here I have plotted all storms at 35 degrees south. You can see all the SEDs are on the left-hand side. So of the diagram, which means almost all of them are right-hand polarized. So let's look at the SEDs from the storm at 35 north. This was the so-called Great White Spot. And here you can see, this is because there were so many SEDs. You have them, each diagram is from the Great White Spot, but lasting typically about a month. You can see that most SEDs, they are typically on the right-hand side. So basically that means all the SEDs from nearly all, the vast majority of the SEDs from the Great White Spot are left-hand polarized. Only a few pixels you can see is the right-hand polarization, and that could actually be due to a contamination by the Saturn kilometric radiation, which I've shown before, because usually Saturn kilometric radiation is oppositely polarized to the SEDs. Here are more diagrams from these storms of 35, the Great White Spot at 35 north, and we also had a storm at 50 north, which also says predominantly it's left-handed polarized. So in total, actually, we evaluated more than 20 million SED pixels. Actually, polarization measurements are available for 1.2 million of them, and actually 400,000 were below 2 megahertz and 800,000 were above it. And within this 1.2 million, we also had to eliminate 400,000 SED pixels due to this low elevation angle between the antenna plane and the incoming wave direction, and due to low intensity. So basically, and this is what I also want to say, is important that which I show here are SEDs below 2 megahertz, and I will show you a little bit later why this is important. Then we had actually a single storm at the equator, where actually we had, which lasted for about a week, and here we only have 8 SED pixels below 2 megahertz. 4 of them were right-handed, actually, and 4 of them were left-handed. And interestingly, the right-hand ones were detected when Cassini was at northern latitudes, and the left-hand ones when the Cassini was at southern latitudes. So how to interpret this? And this is shown in this figure, which shows you Saturn. It shows you the axisymmetric magnetic field, which goes from north to south. I've drawn field lines at the equator at ±35, where the storms are located, ±50s, and ±75. This is where the SKR is actually located in the aurora. And and here you can actually see these black arrows. They show you the magnetic field direction. And the SEDs, they have to propagate through the magnetoplasmas of Saturn's ionosphere. And the ionosphere is a birefringent medium. So basically what happens is you get two modes. You get an LO mode and an X mode, which are defined with respect to the magnetic field direction in the plasma. And if you look at this, actually you can see the red lines show you left-handed polarized SEDs, which you typically see when the SED was in the northern hemisphere. And here also the angle between the K vector and B is smaller than 90 degrees. But interestingly, when you're at the equator, when you're at the equator, actually you see left-handed SEDs only when Cassini was in the southern hemisphere, and right-handed SEDs when Cassini was in the northern hemisphere. The right-handed ones, they are blue here, and you can see when the angle between the K vector and B is larger than 90 degrees, then we have right-handed polarization. And this is exactly how an LO mode is defined. So basically the SEDs below 2 megahertz, they appear as LO mode waves, basically oppositely polarized to RX mode SKR. But it's also interesting to question now, okay, the SEDs are LO mode waves, but where are the RX mode now? So this is actually, you can see the RX mode, and it will come out the RX mode you only see at higher frequencies. What you can do is actually, we look at Saturn's ionosphere. We solve Appleton-Hartree equations, so basically the dispersion relation. We take conditions for a typical conditions in Saturn's atmosphere. Yeah? So we know about the electron density, which is around 10 to the power of 4 per cc, which corresponds to a plasma frequency of around 900 kilohertz. The frequency is variable. We know the electron cyclotron frequency because we know the magnetic field. We know the collision frequency from literature. We took about 1 kilohertz, and we also know the angle because we know where the storm is located between the K vector and the B field. And then actually, if you do this calculation, what you can see is you get 4 different modes. Whistler mode, C mode are not important because they're trapped. We have to look at the so-called O mode and X mode, the free space modes. And here you can clearly see the O mode has a cutoff frequency around the plasma frequency, 900 kilohertz, whereas the X mode here in this calculation has a cutoff frequency of 1.4 megahertz. And additionally, if you look actually in the imaginary part of the Appleton-Hartree equation, you can also see the absorption coefficient. You can see that also at frequencies around 2 megahertz, for example, the X mode absorption is still higher than the O mode absorption. That's the so-called differential absorption. So what happens actually, you see only the O mode at lower frequencies because it has a lower cutoff frequency first, and because it has a lower absorption compared to the RX mode. So basically the RX mode at lower frequencies is absorbed. And you can make a calculation about that, but maybe that's leading too far. But what I want to show you is that if you now plot the circular polarization versus frequency and the linear polarization versus frequency, you can actually see that when you go to higher frequencies, the circular polarization then tends to 0, around 7 megahertz, and also the linear polarization starts to rise. In fact, this is a bit tricky because also the antenna calibration is strictly valid only until 2 megahertz, because then these so-called effective length vectors of the antennas become complex quantity, which depend on the frequency and the incoming wave direction. But only at lower frequencies, when the wavelength is large compared to the dimension of the spacecraft and the antennas, you have this so-called quasi-static regime. Here the antennas are fully calibrated. But basically what you still can see, it seems you have no more circular polarization, because then you start to have a superposition of the LO mode with the RX mode, because the higher you go in frequency, the stronger the RX mode gets. And if they superpose the circular polarization, their polarization, basically the circular one cancels out. And actually, if you look, then the linear polarization, then it depends, do you assume incoherent superposition, which would lead to depolarization? That's actually the theoretical curve for coherent superposition is dashed. But for incoherent superposition, the linear polarization would go to 0, but coherent superposition would mean full linear polarization. So basically what you see is something in between. And this is because, you have different refractive indexes, which lead to different group velocities. But when you calculate the arrival time difference at 1.2 megahertz, it's about 100 milliseconds. And the problem is that these SEDs consist of sub-pulses with a typical duration of 1 millisecond. So if you are at lower frequencies, you will have incoherent superposition. But when you go to higher frequencies, this arrival time difference is just a millisecond, and then you might start to have coherent superposition. But okay, that's a little detail. You can do some mathematics. So let me come to my summary. So Saturn lightning below 2 megahertz is a highly polarized emission with especially high degree of circular polarization. It is right-handed polarized from a storm in the south and left-handed polarized from a storm in the north. The single storm at the equator, which we had in 2005, showed left-handed polarization when Cassini was at southern latitudes and right-handed polarization when Cassini was at northern latitudes. And this behavior actually suggests that we see below 2 megahertz, we see the LO mode, because the RX mode is mainly absorbed below 2 megahertz due to this, what we call differential absorption effect. That's why the sense of circular polarization below 2 megahertz can actually be used as an indicator for the hemispherical origin of the Saturn lightning storm. So it's right-handed from the south, left-handed from the north, and actually opposite to SKR polarization. And that's why with my colleague Masafumi Ima, we actually went back to the old Voyager data and looked at the Voyager SED polarization, but this was quite tricky because the Voyager PRA instrument, the radio instrument, has a very intricate way of measuring the circular polarization, and maybe that's why the thing is not that clear for Voyager. So then the circular polarization goes to 0 towards 7 megahertz, and the linear polarization starts to rise, which then is due to the superposition of LO with RX mode, which progressively gets more and more power. That's it. Thank you very much.
Question to Professor Fischer. Maybe I ask the question first. So there are only thunderstorms at the equatorial region of Saturn. Is that correct?
No, we have at the equator, and actually this was only observed once during the Cassini time. We have these great white spots in history, which usually occur every 30 years. Some of them have been observed at the equator, but the other ones are at 35 north and 35 south. This is called the storm alley. And we also had a storm observed at 50 north. And these are these wind speed minima. So it seems they are confined to certain latitudes.
Okay. Other questions? I see any enhanced raising. Yeah, please. Yeah.
Hi, Georg. Good to see you again for so long. My question is concerning the source, thunderstorm. Is there any difference in the lightning source between northern and southern latitude, or is it just propagation effect?
It's just a propagation effect. I don't think that there is a difference. I actually think that when you look probably because the only spacecraft that observed such lightning at Earth was this Forte spacecraft. So actually what we think is actually when you have the lightning channel, it's more or less, let's say, a linear feature, then it should radiate. If you say the lightning channel is like an antenna, it would radiate linear polarization. So for both north and south. And then what happens is in Saturn's ionosphere, which is a magnetoplasma, you have a birefringent medium, and this in this magnetoplasma you have they get circularized, left-handed and right-handed in an O mode and RX mode. And mainly we see
as a follow-up to what you just said. Yeah. Can you infer if lightning on Saturn is vertical or horizontal?
Probably not. I don't think so. Because it gets circularized in the ionosphere. I think we don't know it from the images. It would be, of course, interesting compared to Jupiter, but I cannot even tell after many years of Saturn lightning research if it's a long discharge or if it's a so short discharge. It's still not known, I would say.
Is it true that there's a difference between the lightning frequency at the Voyager and Cassini?
No, that was a similar frequency. The only thing was the Voyager receiver went up to 40 megahertz and Cassini only goes up to 16 megahertz. But typically, actually, there's no difference. I think that usually when they looked at Voyager data, they inferred also some SEDs in a frequency range of a few hundred of 10 or 20 kilohertz, which in my opinion is a misinterpretation, because we didn't find this with Cassini. So basically, I think the cutoff of the ionosphere, it can go down to maybe 300 or 500 kilohertz, but not down to 10 or 20 kilohertz. This is too low. And that's how it was interpreted in the Voyager times. But I looked at these dynamic spectra again, and there are these SEDs below this SKR region. They are quite, I would say, these are fishy. They are not. I don't think they are real, actually. When we look at Cassini data, where we didn't see this.
Okay, great. Questions? Other questions?
Maybe a remark. I must say that I agree with Georg's interpretation about Voyager. This was partly my interpretation at the time of Voyager, but it was very early in the time of detection, and probably the very low frequency ones are maybe spikes of SKR or whatever else. But yeah, yes. I agree.
Okay, I think I read your paper, so that's why I asked the questions. If no other questions, we could ask the question again, because at the end of the session we still have some time for some discussion. So the next talk will be given by Professor Yukihiro Takahashi, and the title is Lightning Exploration by Spacecraft and Ground Telescopes.
So I want to show my lightning exploration. Namely, it's a Venus here by spacecraft and ground telescopes. So this is the schematic, the imagination of the spacecraft measurement of the Earth with the Japanese spacecraft named Akatsuki, the climate orbiter around Venus, launched in 2010 and arriving at Venus in 2015. So this is the background. As you may know, the existence of lightning in Venus has been a long controversial situation. So some people said it exists, but others not. Even watching at the same data. And for the past observations, the optical measurement, the Venera and 910 and ground-based telescopes results in positive conclusion, but Pioneer Venus, Vega balloons, and Galileo flyby negative. And on the other hand, electromagnetic wave observations, also positive and negative results are reported. So this controversial situation continues over 40 years. But at the time of my consideration, the initiation of the Akatsuki's the project, it's 20 years, but already almost 40 years. And this is our instrument, which aims to conclude this kind of controversial discussions. So it's quite small, but very unique instrument, optical instrument to detect the lightning flash. So the past measurement shows some optical signatures, but no time-resolved the light curves available. So then we designed this camera. Actually, it's not camera, only 4x8 pixels for the lightning detection. But the observation frequency is about the 20 kilohertz, the very high frequency. And we choose the 777 nanometer bands. It's atomic oxygen, which is expected based on laboratory measurement. And this is the Borky results, 1996, using the lasers. So, and 1 bar and 5 bars also showing the very distinct the line emissions at 777 nanometers. And this is our sensors. Half of them are used for lightning, but other half for air glow measurement. Here we concentrate on the measurement of lightning using 777 nanometers. So the whole pixel number is 8 by 8 pixels, but 4 by 8 pixels are used for 777 interference filters on attached on the surface. And then to detect the various kinds of lightning flashes. So at that moment, we didn't know the light curves. So therefore, they sometimes could be very short, like as the lightning flash on the ground in the Earth. So it's order of the millisecond duration. And but sometimes we can see the long duration, such as the sprites, which has the 2 milliseconds up to the several tens of milliseconds, and or the longer flashes like the blue jet on the Earth, so which has the order of the 100 milliseconds. So any kinds of durations and rising time, we prepared a large number of sets for the triggering system. And the sensitivity settings is about the 10 times and 100 times smaller lightning could be detected with our instrument at a distance of 100 to 1,000 kilometers. And from the 3 radii of Venus, we can detect the lightning, the typical lightning intensity in the Earth. So one of the reliable past results is the Hansel et al. Observed by the Grand Telescope in Arizona, and they reported 7 events per few hours. So then this occurrence frequency is order of 0.01 event per million square kilometer hour, and at the time of the 2020 March, so let's see, our measurement is achieved almost the same amount of the million square kilometers, and 100 million square kilometers. It's equivalent to 1 event per our measurement time. So then detection, the possibility is 86%. And then we finally recorded 1 candidate of the lightning flash. But this is a very coincidence with Hansel et al. And but the light curve is quite different from the typical lightning flash in the Earth. So the time constant is about 100 milliseconds. It's much longer than the average in the Earth. And then light optical intensity, it's not easy to estimate because it strongly depending on the condition of the clouds of the Venus. But the intensity is not so big, but duration is long. So total photon numbers is quite big compared to the typical lightning flash in the Earth. So and then this was found not too far from. It's not close to the volcano. So some former studies indicated the possibility of the correlation with the volcano eruption, but it's not true. But we see the location of a location at this red point, which is on the dark area of the Venus cloud structures. But this is only one example, so then we cannot say the definite conclusions. But and then after that, we have been waiting for almost 7 years in total, but we detected only 1 disk candidate. So from this, we need to imagine what happens in the Venus. So sometimes it seems too long durations compared to the Earth. So therefore, one of the possibility of this flash is from meteors. So the meteor may have such a waveform, the light curve. But considering the very bright flash, so it's equivalent to moonlight if we observe on the Venus, on the ground of Venus. So such a very big bolide, the fireball, may have a longer period of the duration, like as the order of the seconds. So, but in this case, it's 100 milliseconds. It's not long enough to explain by the fireball. So, and we found a similar light curve from the data set of the gleams on board International Space Stations. This is from Professor Sato. So he found very quite similar light curves observed in the Earth. So the fine structures is somewhat different, but which has the continuous the pre enhancement and the strong enhancement later, and finally the one or more. It's accidentally similar to our measurement in the Venus. So so far this is our satellite spacecraft measurement, the Akatsuki results, and the another approach is the ground measurement using our ground telescope owned by our university, which has the 1.6 meter reflectors. So, and we choose the wavelengths of the lightning, expected lightning, again 777 nanometer atomic oxygen line, and we to confirm it's from the Venus, not caused by the noises, optical or electrical noises. We prepared another band at the 700 nanometers. So simultaneously, we recorded both and then compared the occurrence frequency of the 777. But the light from the telescope is recorded by a CCD camera to know the place of the target area of the photometer, and then the using the dichronic mirror. So we recorded 777 and 700 with two different sensors, photomultiplier tubes. But unfortunately, up to now, we don't have any conclusive results about the lightning signatures. So we are trying to continuing the observations, but considering the occurrence of frequency of the big lightning flash, if we assume that our Akatsuki result is correct, then we have to wait for more time. So, and then also it's not easy to find the flash in Venus, because most of the time the Venus face is almost the daytime. So the day side of the Venus. So therefore, it's not easy to find the faint flash in daytime. So we have to wait for the very limited period we can see the night side of Venus. And another try is underway. So we are using the event-based vision sensor, which records only the deviation from the previous frame. So then we can easily detect the lightning flash. And then this is the experiment in lab. So we use the banded graph to make the electrical discharge and recorded the images between two balls. So it's quite successful. But this case is 60 frames per second. But in the future, so we can decrease this time resolution. So then we will approach to the order of the milliseconds. So then we expect some signatures could be found by our telescope measurement. So this event vision sensor EVS has an advantage also in daytime because of the deviations. The two frames deviations are recorded output from the sensors. So therefore, we may have larger chance than the photometer measurement in night side. Okay, so then this is an example of the images taken by the event vision sensor watching the moon. So due to the fluctuations by the Earth atmosphere, the deviation is always existing along the crater outlines. Okay. Also this is the stars. Star has scintillations like this. So therefore, always output. But if the star is completely fixed, like as from the orbit of the Earth, so then no records output from the sensors. Okay. So to detect LHC type event with the event vision sensors, we need to change the time constant to output. So we can change 100 frame per second or 10 frame per second. So this is planned to make the future measurement. That's all for the presentation. Thank you very much.
Thank you. Thank you. It's very interesting. The last part is coming from your 1.6 meter telescope, is that right?
It's a grant, yes.
1.6 meter.
Yeah, it's 1.6 meter.
It's
equivalent to the Arizona telescope.
But I have a question. Ivana, you're here. You're still here, not going to the airport.
Yeah, I will just leave in 5 minutes, but I have a question.
Okay, go ahead.
Seeing your waveform, I think it's not completely off in comparison with terrestrial lightning, because if we have continuing current and M components, we see easily several hundreds of milliseconds. So I have seen many similar waveforms from the Fireball photometer array, which is operated by the Astronomical Institute of the Czech Academy of Sciences. So I can plot over your waveform several different waveforms which were detected by ground-based photometers. So I think it's not completely off if we assume some continuing current.
So there, many possibilities to explain such a long period. So
it
could be continuing current.
Explained by continuing current.
Yeah. Thank you very much.
Yeah. So goodbye. It was a nice part of the workshop. I'll see you sometimes later.
Yeah, right. Yukihiro, how about Pioneer Venus Express? Did they see any signal?
No.
Any lightning signal? No. Venus Express.
No, so far, no positive results from the Venus. Venus Express. You mean the Chris Russell? Chris Russell shows some the results of the low frequency measurement, but from the polarization analysis, it's not the reliable we think. So, what do you think, Georg?
We cannot hear you.
Yes, it's also, I think all these Venus, they are also too long, these signals for Venus.
Okay.
But anyway.
Other questions?
Maybe I have a remark, not a question, if you allow me.
Yeah, please.
Actually, I've been contacted by Solar Orbiter people to analyze the data from the flyby of Venus of last February. And so I did exactly the same analysis as we did on Cassini flyby of Venus in 1998 and 99, during which we detected no signature. And in the flyby of February, it seems there is something. So actually, we are now checking for the more distant flyby that were previously there. And probably you will hear about it in the coming weeks or months. I don't know. We have to check if we are not doing stupid things, but there may be interesting signals there.
All right. Thank you very much.
All right. Good. Yeah. So if there are no other questions, then let's go on to the next talk will be by Philip. The title is the ground-based radio search for planetary lightning.
Yes.
It's a new far. Yeah.
Yeah, Nenufar. Do you see my screen or partage it? Okay. Let's see. Yeah, so it's first some warning. It's a talk from a radio astronomer. I'm not specialist of lighting physics. And so it's kind of a mini review of observation of planetary lightning other than the Earth. And then it ends with a call for collaboration, as you will see. So the background image here and the logo is Nenufar, the low-frequency radio telescope that we have now finished building in France and that is operating. I will come to that in a few minutes. So of course, this is a specialist assembly, so I don't have to recall that lightning is acceleration of charges that leads to electromagnetic radiation. And in high-frequency radio, so megahertz to tens of megahertz, which is the range in which I've been looking for lightning, both from space and from the ground, there is interesting information to draw from both the time profile of the lightning at, say, microsecond or millisecond time scale, and the spectrum. And normally, both of them are related. And for example, when the tortuosity of the channel increases, the high-frequency spectrum is expected to increase also, like here. Okay, so I go very quickly through this because Ivana Kolmasova has covered this. There were detections only in visible and Whistlers with Voyager, no HF. And in Juno, microwaves and Whistlers, again, no HF, and some difference with Earth that Ivana Kolmasova has described, so I don't go into more detail on that. On Saturn, Georg Fischer covered that, so let me just recall very basic things from Voyager and Cassini, and then add a few details from the ground. So Voyager discovered the lightning from Saturn, the small streaks here, because as Georg explained, the events are broadband, but the receiver is sweeping across frequency. Cassini had a wonderful observation in which Georg did a lot of very nice work with episode linked to the rotation of Saturn and correlated with storms. And when we studied the detail of the flux density of these discharges, we realized that they are extremely strong and they can reach hundreds of Jansky. So a Jansky is 10 to the minus 26 watt per square meter per hertz. And it's typically one Jansky or a few Jansky is relatively easily detectable with ground-based radio telescope. And this plot on the bottom right is a distribution of the time profile of the lightning from Saturn, measured as the length of the streaks here. And you see that indeed, the overall structure can go up to a few hundred milliseconds again, as we talked before, but there may be substructure, of course, much shorter. As Georg mentioned, there was the giant storms with thousands of lightning, tens of thousands of lightning detected very densely, with a very strong intensity up to 10,000 times the Earth's one. From the ground, as Georg said also, but this is an example, lightning were detected between 2007 and 2010 at the UTR-2 radio telescope in Ukraine. We brought some receivers there, and so we participated to these works. And this is a typical observation. The telescope can synthesize two beams simultaneously in the sky. This is a beam on Saturn, a beam off. And you see very well the broadband lightning that occur here. And we were very happy to see this in 2007. And there were many studies, correlation studies with Cassini. So ground on the top, Cassini on the bottom, and you see there is a lot of correlation when the storm is visible by both. And distribution of time duration of the lightning, quite consistent with what was observed with Cassini. A very interesting measurement is that with waveform measurements, so down to microsecond measurements, it was possible to measure the dispersion of lightning during their propagation across the solar system plasma, so the solar wind. And you know, for pulsars, for example, this dispersion measure that leads to incline the slopes here, dispersion measure is a few units or tens of parsec per cubic centimeter. In this case, because it's very close, it's only solar system, we could measure a dispersion measure of 3 × 10⁻⁵ per parsec per cubic centimeter, but indeed it's well measured here. One question that was raised by Farrell et al. 2007 and as Georg said, it's not completely solved yet, this is the measurement of Cassini radiated power, let's say. It's in arbitrary units as a function of frequency. And the question is, does this correspond to a spectrum that is analog to a terrestrial lightning spectrum, but much, much higher intensity, say 10 to the 3, 10 to the 4 more intense, or supervolts, or does it correspond to this terrestrial spectrum, but shifted to the right because the lightning would be very fast at Saturn, the substructure? Okay, so ground-based measurements from UTR2 tried to address this question, and the results are ambiguous because if you do some waveform capture, so very high resolution measurement, this is at millisecond dynamic spectrum. This is at nanosecond, 100 nanosecond resolution recordings of the time series. Here, you can derive the overall spectrum from this, and you can derive the low frequency spectrum from this time series. And so this low frequency spectrum has a peak at about 17 kilohertz and a slope in f-2, and the high frequency spectrum had a slope slightly steeper than f-1. Okay, there was the finest structure detected here was about 50 microseconds after the dispersion, so the dismirroring of the data by propagation. And this is quite consistent with the peak at, say, 10, 20 kilohertz. There was no isolated peak down to 0.5 microsecond resolution here, and the maximum flux density was kilojensky. So this would rather point at supervolts, so not very fast discharges, and so very, very intense lightning with this kind of energy that agrees with optical measurements. But on the other hand, the high frequency spectrum, in this case, we would expect it to be steeper. So this rather supports a fast discharge, this spectrum that is not so steep. So that's why I say it's ambiguous. So actually, we need more well-calibrated high-resolution type profile and spectral measurements over a broad spectral range in order to respond definitely to this question. Also for Saturn, an interesting question is to study the seasonal cycle, because as Georg noticed, there has been no detection after 2013. And so we are now almost half a Saturn year after the last Cassini detection, and it would be interesting to see the lightning resuming with the season. Now, a few words about the other planets. At Uranus, as you may know, we detected with Voyager some kind of long duration lightning with ionospheric cutoff and with very similar to Saturn lightning, but lower intensity and longer duration. And so this is a kind of sketch of spectra of Saturn electrostatic discharge, of Saturn lightning and Uranus lightning actually in Jansky versus frequency as would be detected from the Earth. So you see that Saturn lightning can go up to a kilojansky typically, whereas Uranus lightning could go up to maybe a few tens of Jansky maximum. Of course, we can observe from the Earth only above the ionospheric cutoff, so to the right of the dashed line here. And so it means we are in a less favorable range with weaker flux density than in space. Venus, I just refer you to Takahashi's talk just before me. So it's very controversial. And as you know, there was no detection by Cassini. And these are interesting measurements, not because I made the analysis and participate to the publication, but because the same instrument flew by twice above Venus in 1998-99, here very close flybys. And then in 1999, slightly later, the same instrument with the same setup flew by the Earth and detected 1100 lightning when flying above the Earth, whereas the detection at Venus were a few units consistent with Gaussian noise peaks. So we concluded from that there was no lightning detected by Cassini at Venus at that time, and that if lightning were present, we could constrain their duration and intensity by this kind of plots. Earth detection is on the top right of this plot. For Mars, situation is also controversial. There have been papers from Mars radar experiment from Gurnet and others, and it is expected that there may be electric discharges in dust storms And there were studies, for example, by Farrell et al. In 1999 of dust devils on the Earth that produce indeed electrical discharges. And so it could be present also on Mars. So in 2004, I tried to group all that was known online. So there is no information from Juno measurement on this plot because it was done well before. So this plot tried to gather the spectra, so flux density from the Earth versus frequency, from Saturn, Uranus, some kind of range for Venus lightning, Jupiter, upper limit, Uranus, and so on. And I tried to overplot. So this sensitivity curves at the time, it was before LOFAR operation, when it was construction. They were a little optimistic. And this is actually the sensitivity limit that is reached by LOFAR core. Only the core of LOFAR, I will come to that in 1 second, is adapted to observe lightning. And NENUFAR, to which I will come in a few more minutes, has a better sensitivity that could, in principle, give access to Saturn and Uranus lightning. And SKA, that is coming in a few years from now, but that will observe only, unfortunately, above 50 megahertz, should have a like 2 orders of magnitude better sensitivity, so which will be very interesting, of course. So what about these ground-based measurements? The LOFAR radio telescope is an array of sensors of very simple antennas that is spread across all Europe. It is the first new generation radio telescope and SKA Pathfinder that observes in the range from typically 30 to 80 megahertz with an extension possible to 10 with lower intensity and 110 to 250 megahertz. In between, you cannot observe because there is the FM band. And it is a standalone beamformer and imager and with multi-beam capability. And it is made of many so-called stations. And only the core can make high time resolution measurements, so it's well adapted for lightning. The core is 3 kilometers in the center of Netherlands, and it has a resolution, angular resolution of 4 arc minutes, for example, 80 megahertz. And LOFAR is really a multi-scale structure. So this is the overall European instrument, a zoom on Netherlands, the core that is adapted to lightning observation. And then in the center of the core, you have a super TERP, so-called, with 6 stations. And stations are groups of high frequency and low frequency antennas. And these antennas are fixed. One antenna sees the whole sky. And then combining the antenna, you make beams at the station level. And you combine these beams at the core or array level to make small, very narrow beams or images with narrow pixels. And this is the range that is covered or frequency covered by LOFAR. So with LOFAR, actually, we could have lightning observation of Saturn only during the commissioning time. Because when LOFAR started observations, very shortly after, lightning occurrence stopped on Saturn, as Georg said. And so we had measurement in 2010, which were very early and not so sensitive measurement. So we tried basically to process the data between this range, 1575 megahertz at 80 microsecond resolution. We tried to process this in order to find spikes, so quick variations over typically millisecond time scales that were present in the on-beam and not in the off-beam. This is a kind of number of events detected at versus time. This is hours. And actually, I put this plot because here below, I tried to synchronize with Cassini measurement at that time. And you see that this detection is globally consistent with the occurrence of a storm from Saturn at that time in view. But we could not really correlate one-to-one the lightning events. The viewing was not favorable enough. So actually, we did not publish. We were lazy. We did not publish these results. And there were even later observations in 2011, this time with 5 stations from SuperTop, but coherently summed in the range 2070 megahertz. Again, we had this kind of detection of event during a few hours. And if you superimpose Cassini, there is again good coincidence globally on the occurrence, but we could not, again, due to visibility, correlate one-to-one these events. So the distribution of time were also not inconsistent with lightning. So we could have published that, but we didn't at that time. And there was nice UTR2 publications on which we concentrated at that time. Okay. We had the target of opportunity time later, but it was not exploited because just Saturn was not active anymore. Okay, then in the recent years, we built in France the Nénuphar radio telescope. Nénuphar overlaps the low frequency band of LOFAR and goes really down to 10 megahertz to the ionospheric cutoff with a very good sensitivity, better than LOFAR's core actually. It's made of 2,000 antennas, mostly spread in a 400 meter diameter field in Nancy in France, and then there are a few outliers to do some imaging with arc-minute resolution. So this is the concept of Nénuphar. It's installed around the LOFAR station in Nancy. It's made of 96 arrays of 19 antennas. There is an analog phasing, then digital phasing, and the instrument can work as a beamformer. That is what is of interest for lightning search. It makes time frequency plane recordings with 4 Stokes polarization. It can also make images and catch waveform capture. That is also of interest. So it's a nice instrument that's now is fully operational. And this is a view. So this is a view from the top. So this is the arrays of 19 antennas, and it's kind of both a standalone radio telescope and a superstation of LOFAR. It's also a SK Pathfinder with an effective area of 60,000 square meters at 25 megahertz. It's a standalone beamformer and imager with multi-beam. Okay, the core, the range is 10 to 85 megahertz. Angular resolution is indicated, and it can go to very high time resolution, down to 0.3 millisecond for full spectra, and also waveform capture is possible down to 5 nanoseconds actually. Sensitivity is larger than LOFAR, except in the very peaked central frequency where LOFAR antennas are sensitive. But it's more sensitive than the LOFAR core. And so we have many science cases that are ongoing now with Nénuphar, studies of Jupiter decameter emission, pulsars, exoplanet radio search, cosmic dawn, and so on. And we wanted to start a planetary lightning program. So in the early days of Nénuphar, we started to collect observations on Venus, Mars, Jupiter, Saturn, Uranus. And this is as a function of time since the beginning of 2020. So this is year 2020, 2021, 22, 23, and 24 finally here. And you see it stops at mid-2024. This is a number of hours observed for each target. You see that we have a pretty large number of hours, about a few tens to 100 hours per target, totals 500 hours collected, with 10 milliseconds times 3 kilohertz resolution with full polarization. And interesting thing, we don't have any angular resolution, of course, because a few arc minutes is larger than the planet as observed from the Earth, but we have one beam directed toward the target and 3 beams distributed around the target that are reference off beams. And all the data has been reduced because the data rate of the raw observation is extremely high due to the high resolution. It's something like 250 gigabytes per hour. This is so-called L0 raw data, level 0 data. And all the data has been pre-processed, which means cleaning any narrowband interference and then integrating over 200 kilohertz bandwidths. So we have pixels every 200 kilohertz between typically 10 and 85 megahertz in total flux and circular and linear polarization. And this is so-called level 1 data that is about 3 gigabytes per hour, and this data can be stored forever. There are inspection plots produced at the reduction, and then science data analysis can start. This is an example of inspection plots. This is the raw data for 1 hour, for example, in half of the instrument band, so between 20 and 57 megahertz here. So you see there are a lot of interference, of course, of various kind. The range is less than 3 dB above the background here. This is a flag that are computed at the reduction of the data. And this is the processed data. Now you see the intensity range is stretched over less than 1 dB above the background. So you see very faint emission that are A-team sources in the side lobes and whatever. So you have a lot of junk here. And this is a comparison of what we have in an on beam and one of the off beams. And so you see it's very similar. And what we expect is that the post-processing is, for which a first pipeline does exist, compares on and off spike occurrence and statistics in order to determine if we can detect spikes from the target and not from local sources. But the problem is that the team on planetary lightning on Nénuphar was extremely small, mostly Jean-Mathias Grismeyer in Orléans and myself. A few others were interested, like Baptiste Sekoni, Georg, Igor Kravtsov in Ukraine, but could not spend time on analyzing the data. And actually this team, the core team, I would say, has been presently absorbed by other project, which is exoplanetary radio emission that we start to detect with LOFAR and Nénuphar. So it's super exciting, of course. And the result is that the post-processing and analysis of the lightning data is stuck. And the observation is in pause since May 2024. But it is ready to restart if or when active people would join. And this is my last slide, by the way. So it is a kind of open call. How to get involved if you're interested? You can contact the PIs, so Jean-Mathias Grismeyer or myself here. You can participate to analysis of existing data that are already reduced and ready to be further analyzed. You can, of course, respond to the widely advertised semester call for observation of Nénuphar, either joining our key project or by an independent open time regular program proposal. It turns out that the next deadline for the next semester, cycle 7, that will run from 1st of December of this year to 31st of May of next year, the deadline is in 2 days now, so it's a little short, but there will be a deadline in 6 months. But target of opportunity is possible if some observation, for example, from amateur or from optical professionals tell us then lightning activity is resuming in Saturn, then it's possible to contact the Nénuphar Ops address and ask for target of opportunity. That is very easy to get with Nénuphar because at low frequency you cannot do millions of programs in parallel. And it is also possible, although it has not been done yet, to use Nénuphar for terrestrial lightning observation. So this is actually a kind of call to the community. If you're interested in lightning and interested in analyzing radio data and doing radio observation in the range 10 to 85 megahertz, please come see us. You're welcome. If not, we have to wait that we have more advanced with our exoplanetary project in order for us to come back to lightning observations and hoping that Saturn will resume activity. And a final note, you may have seen in the literature papers about exoplanetary lightning for extrasolar planets. If you have questions, I'll be happy to respond. All this is junk. There is no lightning detection from extrasolar planets. Thank you very much.
Your last sentence, you say there's no hope of detecting lightning from exoplanets, or it hasn't been in observations yet?
Actually, we had, I participated a few years ago to observation at GMRT in India of transiting exoplanet that was, I don't remember, I think it was HG 189733, I'm not sure. Okay, this is a paper by Le Cavalier des Étangs et al. I can tell you. It was, yeah, 2013, I guess, or 9. Okay, I don't remember. Oh yeah, it was maybe HAT P11 or other. Anyway, we had a paper in which we saw a very faint. No, yeah, it was HG 189733. We saw a very faint decrease of the flux density of the system when the planet was transiting behind the star. So we said maybe we have detected a transit of the planet behind the star with a decrease of the flux, but it was a 2 sigma. So we were very careful in the paper saying we are not sure at all of that. And then some other authors that you can find in the literature took this data and say, oh, but this can be a real planetary signal that would come from lightning in the atmosphere. And they made calculation just forgetting that our data were integrated over 30 minutes, each of our data points. And so there was a kind of 30,000 factor dilution of the signal, if any. And so in order to explain our observation, you would have to assume that there are billions of lightning simultaneous at any time in the atmosphere, which is a little excessive to me. And so I don't expect this to be true. And so there were a lot of publicity around this, but I think it's really not serious. So no, because of the short duration, we don't have the sensitivity, even with SKA, to be able to detect such short events in an atmosphere of an exoplanet. But there are very nice prospects for solar system planets.
Okay, thank you. Questions for Philip? I mean that. Oh yes,
Yes.
Philip, go ahead.
Well, Philippe, so if tomorrow the amateur astronomers would see a storm on Saturn, would you be ready to observe it?
Yes, definitely. Yes, definitely.
Okay. Because I'm really wondering, because I mean, it's now almost 12 years that we have not seen any Saturn lightning.
Exactly.
And also the amateurs did not see much storms. I mean, I think there was one in 2018 at higher latitudes, which was published by Agustin Sanchez La Vega. But if I remember, Slava Sakarenko, they made some observations with you there too, but didn't see anything. In fact,
no, not after the published ones. But indeed, in the low frequency, actually, because there is not an infinite number of science programs that can be run, the pressure on the telescope time is, I would say, slightly larger than 1, but not much higher than 1. So if there is some interesting target of opportunity observation requested, we can always find the time to fit in the schedule. So the response is definitely yes.
Okay, that's good. Good to know. Thank you.
Philip, you could send me maybe a poster or something. You know, we could post it for you to see whether there are people interested in this. Yeah.
Yeah. Excuse me, I didn't understand you.
If you have more information on this new far,
Nenufar, yeah.
You're advertising it. If you could send me some more information, maybe I could distribute that for you. Yeah.
Okay, I'll send it to you. Okay.
Yeah, Huang.
Yeah. So I have a question about so I know the deadline. I mean, the proposal call is due in 2 days, but is there proposal template so we can kind of see it, you know?
Yes, of course. If you go to the, I can let me share my screen 1 second.
Okay.
Again. Yeah. You see my screen? No. Let's see. Yes, you see my screen. Yeah. So if I go to if you go to nenufar.ops-norce.fr, you go to the astronomers page. You have the proposal templates here and the call that is here.
Okay.
So yeah, and actually because the time is extremely short, let's assume that you're interested. My advice would be contact me, and we try to put up a very quick and dirty proposal just to insert it in the loop, and we can do something indeed. But it's only if people have time to analyze the data afterwards, which unfortunately we don't have this time.
Okay, just if we have student or researcher, very into the field and they want to take a look at the data.
Sure. Another possibility is to look right now at the existing data. As I said, we have 500 hours. So it's a very good database that allows to train. There may be signals in this data, maybe. But and so it's possible to work with that and then to ask at the next call. It's also very possible.
So it's where, can you point it out, the existing data set is still on that website?
Just contact me on offline and we can discuss this. Yeah.
Okay. Yeah. Okay. Thank you.
Absolutely.
Okay.
I could send you Philip's email address. You know. Anyway, he's so famous you could find it anywhere.
Okay.
Sure.
Yeah. Thanks. Yeah. Thanks.
Thank you very much.
Yeah. Thank you. Good. So we will keep this question if there are any more to the end. Now we will have the next talk by Yayish. Are you ready?
Yeah. I'm now back from the other activity.
Yayish. So Professor Yayish Papari from Physical Research Lab, Amitabha. He's going to talk about past Venusian missions and Venusian lightning. He's going to explain the secret and history, the mystery of the Venus lightning.
Yeah.
Okay, please go ahead.
Yeah, thanks for the opportunity. Is that screen visible and I'm audible?
Can you make it? Okay, it's full screen now. Yeah, please go ahead.
Yeah, so my apologies, like I was late and in other schedules I could not make up in time. Primarily, our activities have multifold at my group, where one of the research activity which we are working is the Venusian lightning. So in this short presentation, I would touch upon some of the past Venus missions, interest to the Venusian science and further exploration as far as the lightning is concerned. So that outline of the talk is like past Venus missions. Is Venus is actually most explored planet, but probably the least understood planet in the sense, in some of the science aspect. Then we'll see the need of the future Venus missions, looking at international scenario also. And then Venusian lightning, and then some of the, basically, though it is a controversial, as we know all of us, but some of the observations, they say there could be the lightning or electrical discharges on the planet Venus, and then how a future observations should be planned, which is immediate answer from the past observations. So this is the cartoon of the solar system. We have inner planets like Mercury, Venus, Earth, Mars, and other outer planets. And other planets are also known for the lightning, like Jupiter, Saturn. Lots of lightning we expect. And as earlier speakers also spoke about the lightning on Venus or Mars as well as the Earth. So lightning on the Earth is because of the water ice cloud, and the physics of the lightning is almost well understood. Of course, the spectrum of the lightning on Earth is still not fully understood, and because of this reason as well, we also study the lightning on Earth. While touching of the lightning on Mars, we have certain activities about the lightning on Mars as well, where the source of the lightning is the dust devils or dust storms during the southern hemisphere summer time, where lots of dust activity and tribal electrifications happening into the dust devils could lead to probably, but it is still the open question, because there are no experimental evidences of or we say in situ measurements of the lightning. Like for example, earlier 2020 there was InSight magnetometer, and with our collaboration with Professor Russell, we explored some of the data from InSight magnetometer to investigate if the lightning occurs on Mars or not, for example. And for the given data set or observation period, we actually could not find any electrical signatures using the InSight data. And the question is still open. And while coming back to the lightning on Venus, the lightning on Venus is expected to be similar to that of the Earth. However, the physics is still not fully understood, or in other words, the modeling of the electrostatic clouds of the Venus that requires certain efforts further to explain the source of the lightning itself. And beyond that, we need to understand or like explore the propagation of the waves, including those Whistler waves, which are very famous for the detection, and then further the instrument design itself. So in summary, like for the lightning as a source of the lightning, the propagation of the waves in the ionosphere, particularly in the night side of the Venus, there are ionospheric holes and interplanetary magnetic field, and plus the detection at the satellite altitudes like 200-300 kilometers. All of these three are having open questions or need more research to fully explain or close down the mystery of lightning. So it is a controversial, but there are reports. So before I'll go to the subsequent slides, a few slides about the introduction and the past missions. So we know that Venus is one of the interesting planet and Earth's sister or twin sister, we call it, and it is probably expected to be formed at a similar time as that form like Earth. And it has an atmospheric carbon dioxide cloud and is shrouded and very much covered. And it is also famous for the super rotation, like it's like a 4 days it is repeating. Now the interesting part is following, like it has 96% of the carbon dioxide, But what happens is there are about 100 to 150 ppm sulfur dioxide SO2, and plus a few ppm level, 3 to 5 ppm is the H2SO4 droplets. And this carbon dioxide and CO2 makes it dielectric, and breakdown strength we can estimate, which we have some experimental setup in nearby university also. And H2SO4 droplets actually reduces the lightning strength, but because of this, magical droplets, basically it reduces the lightning strength, so sometimes it could be faint. Before I proceed, I would suggest to say that okay, I expect the lightning could be there on the Venus. So if there are opinions that there is no lightning, then this slides could be useless for them. But those who believe or investigate, yeah, I believe that it could be present. But what are the reasons for that? Is one of the reason is this H2SO4 amount, which is varying at different altitudes, can lead to the changes in the breakdown strength of the source, or typically it is about 1 megawatt per meter. Rest we know very well, like 90 bar surface pressure and very hot and like that. Now, if you see this slide gives us the past missions of most of the missions are tabulated here. And some of the interesting missions are Bepi, Colombo, Cassini, not to the Venus, but flyby and like that. And the story started from 1962 as a Mariner to flyby, and the agencies have been mentioned here. So we see there are lots of missions to, like Venera 12 is also interesting because of some of the observations which I'll discuss. So about 46 or plus missions have been sent to planet Venus, either successful or failed or passed flyby, and many of these are included. Primarily also because of the gravity assist from the Venus for the outer planets, basically. But still, it is not fully understood or well established, in a sense, like many of the science research problems are open, and it keeps on extending the curiosity to the community. If touch the Akatsuki, which is the recent mission which has ended in the lesson past, was actually operational 2010, and there was a insertion orbit insertion attempt in 2010 which could not be made, and then later on there was insertion on the orbit of Venus on 7th December 2015, which was successful, and then subsequently it provided lots of data observations in many instruments. Primarily, lightning had one of the target of the Katsuki mission, and it was having a lightning and air glow camera LSE on this, where one of the channel 777.4 nanometer lightning channel was dedicated for the observations of the lightning on Venus. And there are other observations, other instruments were also there, like infrared IR1, IR2, and so on. And it has provided lots of other observations, including the radio science data, and also touching that meteor layer V0 in the Venusian profile, electron density profile. Another mission is the Parker Solar Probe is ongoing. In a sense, it had a flyby and some of the observations, but it provided related to Venus, some of the observations provided. But this is not the lightning. It has given one of the result as a circumsolar dust ring, which is in the orbit of Venus. And Bepi Colombo also had some other objectives, but they provided certain other information, like the atmosphere of the Venus, despite being non-magnetized, is capable of withstanding the solar wind under the low dynamic pressure. It's one of the important outcome came from the Bepi Colombo results, and many things could be further followed. And then another mission is the Solar Orbiter, which was not to Venus, but towards Venus, I would say. And again, it has one of the results which provided is the dust impacts are more towards the Venus. But why there is a need of the future missions, despite so many missions, like around 50 missions we are talking now? So the reasons are because of the research gaps which exist in the following points. Like, for example, the formation, the spin, the surface evolution, runaway greenhouse phenomena, surface, subsurface features, process. Then another is the superrotation, lightning itself, habitability, and the formation of the ionospheric layers,
effect of interplanetary dust, interaction of the solar wind, radiations and solar wind and the ionosphere basically. So from whatever information we have on the public domain, we know there are some of the missions which have been planned for the Venus in near future or coming years. So, and some of them are on hold also, but whatever we know, I'm just showing here is a Veritas Venus emissivity, radio science, sensor, topography and spectroscopy, which is expected to be launched in 2031 as going to orbit Venus to gather the data on how the paths of Venus and Earth diverged, how Venus lost its potential to be habitable world, and so on. Da Vinci, the deep atmosphere Venus investigation of novel gases, chemistry and imaging, is expected to be launched around similar time as per the available information. Is initially going to explore the top atmosphere of the Venus, and then it will drop a probe towards the surface. ESA announced a vision to make the detailed observations of Venus primarily using the high-resolution radar mapping, because radar, the microwaves can penetrate those thick cloud layers, and therefore radar could be one of the interesting instruments. Despite repetition, it could provide the surface information, and also it has the objective to study the atmospheric studies. And similar time, again 2031 or so. And ISRO solicited the proposals of different science payloads. So its initial orbit of the Venus orbiter mission could be 500 to 60,000 kilometers, and expected in the near few years, basically. And another is the Venera D is a proposed recent mission that could include an orbiter as well as a lander, and it may be in 2036, later in the coming decade. So what are the science which we can talk about in future based on different instruments is the surface science of subsurface emissivity and the thermal emissions from the Venus surface, and the cloud monitoring, lightning and the cloud top study, air glow imaging, radio science experiments, ionospheric plasma parameters and neutrals, study of effect of interplanetary dust on the ionosphere, plasma waves, solar wind interaction and the habitability. And nowadays people are also talking about the sample return mission, or collecting the sample from the atmosphere or clouds of the Venus. So coming to a little focused point which everybody, almost all of us are knowing or familiar with, is the Venusian lightning. So lightning on the Venus, is expected to occur in the sulfuric acid rich cloud, which are located around 40 kilometers to about 70 kilometer altitudes. So if we compare with the Earth, it is Earth cloud is 2 to 5 kilometer altitude versus about 40 to 70 kilometer altitude. So altitude is very large, high here, and therefore ground reflected ray is not expected much. But what is expected is the cloud to cloud lightning on the Venusian clouds. Okay. Now, why further lightning is required? Because there are past observations, like PVO had certain observations at 4 different channels. 100 hertz is a Whistler channel, and 730, 5.4 kilo and 34 kilohertz Alara channels. Then Galileo had some observations, attempted some observations, but later on it was denied. Similarly, Cassini had some observations, planned observations, but it could not detect, as one of the speakers also mentioned. So points are like there are some signatures and some absence of the signatures, and the reasons could be many. So, and therefore the lightning is actually the controversial in case of Venus. However, on the other side, if we see the Venus Express, it has provided 64 hertz Whistler channel observations using flux-cut magnetometer. And Akatsuki recently has also provided one signature. I will show the slides here. So, and then here in this cartoon middle, it is the typical lightning signal, which is actually artificially generated here to explain the process. Is a time domain signal, and which we have to do the time frequency localization in this spectrogram, and it has to be a running spectrogram. So as the time runs, we are overlapping the samples, and we see some yellow, higher energy signals present here during this time. On the y-axis, it shows frequencies present. So this is a typical signature everybody is familiar with, and because of the dispersion in the ionosphere.
Now coming to the past observations, till now in the summary, there are 5 observations or efforts which I have shown that yes, the lightning is present or could be present in case of Venus. So one of them was the ground-based optical observations. The report, the only report is Hansel et al. 1995. Using ground-based telescope, they attempted to observe the lightning at 777.4 nanometer, and they observed 7 flashes with optical energy estimation of the order of 10⁹ joule. And this is a cartoon showing the night side of the Venus, where the locations are projected because from the observation points to the Venus globe. And there is certain specialized arrangement is to be made to observe, because Venus is a very bright object, and only night side can be observed probably for possibility of the lightning. But that is one of the signature of the lightning there. And then other report is the Venera 12 mission, is Unformality 1979. Paper says, this is the paper right side here. It is a 4-channel measurements by Venera 12 mission. It provided the electrical signals at 10 kilohertz, 18 kilohertz, 36 kilohertz, and 80 kilohertz. So it's like Venera 12 altitude above landing site in kilometer they're showing, and these are the pulses they reported when it passed through the cloud layer basically, and it gave the positive indication of the lightning. Further followed by the PVO OE orbital electric field measurements. So Scarf et al. And many papers were there, and it was also otherwise as well in the domain. We see many papers at that time after PVO that lightning is there. Others says no, there is no lightning. There are plasma waves. But one of the report which says the like Scarf et al. This says the lightning presence, which showed the observations, and there are many other papers at 4 channels: 100 hertz, 730 hertz, 5.4 kilohertz, and 30 kilohertz. And 100 kilohertz happens to be the Whistler mode, because the gyro frequency on the Venus is 560 hertz. So below this are Whistlers, which provided one of the observations of the lightning. So like for example, we are having a similar activity for the lightning detection. So like this is one of the reported work at 2018. So we use a short dipole antenna, and then there is a filter to remove some of the interferences, and then we use a preamplifier, and then we divide the signal into different channels. Like PVO had 4 channels, we can divide into multiple channels based on the signal strength and the resources or complexity allowed into the instrument. And then we can use the microprocessor or FPGA to process those signals. Or if this block is a PVO-like architecture, and if we don't want to do that, like discrete filters, then probably we can do directly the high-speed 2D conversion, and using DSP processor, we can do the filtering and on the software using the data also. Then one of the other positive indication of the lightning is the Venus Express magnetometer, which provided 64 hertz Whistlers at about altitude 250 kilometer or less, and a few papers also exist in the literature which shows these are the 3 magnetic field components, BX, BY, BZ, and some of the pulses they reported, and the further analysis, not only this but further analysis also there in their paper, are showing that these are the lightning generated signals. And but there is another things coming up also because of the Parker Solar Probe, which I want to share. Maybe there is no slide, but Parker Solar Probe observations in the vicinity of Venus, about 2,400 kilometer during the flyby, they said they found some of the Whistlers which are traveling towards planet Venus. But if the waves are traveling towards Venus, then the source cannot be the Venusian cloud, because Venusian cloud lightning is the source. Then the waves have to travel away or out from the Venus planet. But these waves detected by PSP, they are traveling toward Venus, so they are also expecting. But the warning here is that it is at 2,400 kilometer like altitude or distances, And it is not the ionosphere, or we talk 200, 300 kilometer altitudes. So there could be something else, or there could be both also as a possibility. And finally, there is a recent observations, the paper by Professor Sanformality. It is the observation from IR2 camera on Akatsuki, is saying that at 2.26 micron, there is a flash they have reported, which they say is, is lightning on Venus, basically signature. So all these 5 observations, ground-based observations, Venera mission, PVO, Venus Express, and Akatsuki's last result, all taken together indicate the possibility of existence of lightning or electrical discharges in the Venusian cloud. But because lightning, it's an opportunity-based observations. So, like for example, optical flash satellite has to be present at that time. Like due respect, Akatsuki had a very different orbit. So when it comes near periapsis, lightning should have occurred at that time, because it has very small time for the observations. But it doesn't say yes or no, actually speaking. It means that the question is still open. And this is directly outcome of this, whatever we talk, is that in the future, if we want to close this controversy, we actually should have simultaneous observations of this 3 domain signatures. Like we should attempt electrical field observations, magnetic field observations, and optical or IR also. And that could also be added along with the ground-based observations. Coming to our, this is the last slide. For the ground-based observations, we have also a proposal of observing this lightning on Venus from the ground, from our observatory at Mount Abu, Rajasthan. So that proposal is in pipeline, and that is the work similar to this Hansel and these people work. So that also we are trying to carry out in near future. Thank you.
Questions to Yash? I mean, he's a believer in Venus lightning. Yukihiro, you have a comment?
Yeah. So I myself, I'm not sure if the lightning exists or not. But so far, so my data suggests the existence, but it's not 100%. We need to still continue the examination.
But that question, how come the Venus does not have lightning as often as the Earth, right? Like Philip, who said that the last time when is it Cassini or Cassini, Philip, the same instrument, so Earth passing Earth, so thousand of lightnings and not a single one at Venus.
Yeah, I think at least the occurrence frequency in Venus is quite small, and therefore the statistically the Cassini or Galileo may detect something, a kind of accident. So it's the statistically it's impossible to find the lightning signatures.
Okay, Philip.
Yes, I agree with Professor Takahashi. Actually, I find quite fascinating that, for example, at Saturn or even Uranus, we don't ask ourselves the question, lightning do exist. We are sure of that. So why are we sure of that? For example, because at Saturn, we have clearly observed a variable ionospheric cutoff. So this is a signature that is perfectly clear. Also, we have observed temporal modulation with the rotation of the planet. So, of course, what Jayesh Pabari proposed, that is simultaneous observation with optical and so on, is very nice. But I think that maybe, if we are lucky enough, in radio, some key signatures like ionospheric cutoff, of course, from space, because from the Earth we have the problem of ground-based ionospheric cutoff, or temporal modulation, are key signatures that could eventually lead us to conclude. But for now, I agree that we don't know. We still doubt if it's there or not.
Okay, yeah. Go ahead.
Just one aspect is about the typical dimensions and microphysical properties of the clouds on Venus. So basically, they are stratiform in nature. And we know that from terrestrial perspective, stratiform clouds seldom, if ever, produce lightning. So we need convection. And in Venus, stratified, stable atmosphere, there is likely no convection. And even the theory that maybe volcanoes and orographic induced local convection may be responsible for lightning. Actually, as Yukihiro had said, the location of that single flash does not conform with orographic, for example. So my point is that lightning may be very rare in Venus, but not as frequent as, for example, Russell deduces from the VEX data.
No. Okay.
Yeah.
Thank you. I think that we'll sooner or later we'll come back to this question. Okay, the next one. Yais, thank you very much. And then you spent a lot of time on this. I think that I hope that you will be paid back. So the next talk will be given by Yukihiro. I already explained that his talk title is the microsatellites for lightning research.
So this is not a paper on the results of our measurement, but just an idea for the future project. So we are developed. So we have been doing the lightning research, especially on the TLEs or the Venus exploration, together with Yoav and Georg and other scientists in the world together. But on the other hand, my initiation of lightning study is the TLEs, on the ground. So, and then we have been working also with Yoav so many years. So, and on the other hand, we developed a microsatellite for sprite studies. But now we are developing more satellite for the remote sensing, general purposes. But here I want to suggest to utilize this kind of tools for the lightning and the thunderstorms, not only the lightning discharges, but also the thunderstorms, which may impact on our human life. So this picture shows the 50 centimeter and the 50 kilogram microsatellite just released from the International Space Stations. It's not computer graphic. It's a real picture taken by an astronaut. So our activities on microsatellites is induced by the lightning, the TLEs like this. And this is the aircraft measurement using the jet airplane, and capture so many pictures from the airplanes from side. And like this, so many variations. It's fascinating. But the next step is to monitor the captured images from just above the sprites. Then that was 2005, just right after the success of the Formosat 2 imaging of the sprites from the side. So many pictures are already given. But the next step is to find the horizontal structures from above. Then this race was started 2005, and the French team has an advantage because they already started the Taranis project with a weight of 150 kilogram small satellites, and then the U.S. and Taiwan and also the ESA started think about the sprite measurement imaging from above. So then, how to win this race? My idea is to build the microsatellite inside our university. So this is the first success of getting much budget to build the satellite, the 3 million euro at the time. And then the students make it like this. The manager is a up left woman, and the right bottom is my boy student who built the cameras for this. So, and then after graduation, they got married. So because of the close relationship, building the satellite. So then this is the first images captured by our Sprite sat, but unfortunately, right after this imaging, the satellite got sleep. I'm sorry. So then, but I know just now the microsatellites is a very strong tool to investigate the space and the Earth. So the cost is about 100 times cheaper than the typical satellite, big satellite developed by the space agency. And only 1 or 3 years are enough to build it. And then, but observing the lightning from the low Earth orbit, the problem is the observation frequency. So sometimes the famous Landsat satellite visit a certain place only every 16 days. But we want to see the every day or even throughout the nighttime. But it's not easy. But our satellite has the ability to look at specific points almost every two times at nighttime, every two times at daytime. So the pointing accuracy is achieved to be 0.05 degrees, the top quality in the world. So therefore, if we know the active thunderstorms based on the ground measurement, then we can see the thunderstorms from above simultaneously. And this is another example of our satellite, 50 centimeter cubic, and we carry the 5 cameras on board together. So it's not impossible. So then we, Hokkaido and Tohoku universities, developed already 6 satellites and launched them. And except for the first one, we almost succeeded in capturing good images. And one of them, the RISAT, launched in 2018 as the collaboration between Taiwan and Japan. And this is the example of the cameras on board. We can select any colors, any bands using the liquid crystal technologies. And only one camera can choose the 600 bands. And this is the very successful image, the world records of the ground resolution, 3.7 meters at the selectable 600 bands. So that was developed by the National Central University of Taiwan. And the left side is the very impressive images, much better than Sentinel-2, the very expensive satellite, the Earth observation satellite. And then now we are applying this technology to the weather atmospheric studies, especially to predict the thunderstorms or the torrential rainfall caused by the rain ban. So we need to know the distribution of the water vapors, especially in the ocean. So then there is not sufficient number of the satellites exist for the water vapor measurement now. So we want to make the low-cost satellite which can measure the water vapors easily. So one of the try is our measurement with the narrowband filters using the liquid crystal filter to capture the absorption band of water vapors from the satellite. Then we confirm that significant absorption can be seen and on the ocean. So therefore, it's just a column value of the water vapors, but it's a very effective to know the water vapor flow over the ocean. So this could be combined with the lightning measurement, and then also adding to this, we want to know the development of thunderstorms, which will be compared with the lightning activities. So, but unfortunately, only with the existing satellite, we cannot know the height of the thunderstorms because of the assumption of the temperature profile is not valid for the thunderstorm area because of the strong updraft and downdraft. So, but if we measure the thunderstorms from different angles, then we could make the 3D imaging. So this is our ground measurement systems. We have the several, almost 10 stations in Southeast Asia, including Japan and Thailand, Taiwan. So then we determine the location of the lightning, the big lightning. Almost the detection efficiency is about 10% or somewhat less than that. So then we installed the 10 stations in the Philippines, and also in the Metro Manila, we installed the 50 sites, observation sites, under the international collaboration with the Philippines. So and then we can geolocate not only the geolocate the lightning positions, but also we can estimate height of the charges released from the discharge. And then we can estimate the charge moment changes and also the height distributions of the thunderstorms, which will be compared with the thunderstorm development, I mean 3D structure of the thunderstorms. That could be very useful and effective to know the further precipitations. And then my idea is to combine the ground stations and the ground radio wave stations to determine the location of the thunderstorms, and also the microsatellite operation, the on-demand operation to make the 3D structures of the clouds. So this is an example of the 3D model of the clouds measured by our satellite developed by the Philippines students. The world best resolution, I think, at the time, so to know the structure of the thunderstorms. And right side is reproduced the color expression, and left side is Himawari, the very expensive geostationary meteorological satellite, which has the 2-meter resolution, but we achieved already 100 meters or less. So much better than the Himawari. And then this resolution is required to know the thunderstorm development. The 2 kilometers too huge. And then this is another product. So this 3D model are made based on only 10 seconds measurement. It's impossible even with ground radar systems, cutting edge radar systems, with using the K-band. So, and also we want to know the prediction. We want to predict the intensity of typhoons. But unfortunately, for these 20 years, the accuracy of the typhoon intensity is decreasing. It's amazing. So even though there's so many trials with the high-speed the images, so many images taken by the satellite and also the ground measurement and the supercomputers. But the prediction is becoming worse, even worse, these 20 years. It's amazing. So, but one of the reasons is that we don't have any ways to know the center pressure, the measurement directly. So, but here I want to suggest to make the 3D modeling of the clouds, eye clouds of eye wall by the microsatellite. So then if very intense, it's very steep, and we can see the ocean from the satellite. But after that, the typhoon intensity is becoming weak, and then we can see the shallow and the big diameter clouds. So then if we can observe this, and we can say that this is how much is this intensity. The intensity means the central pressure, and it's not perfect, of course, but good signature, the hint to know the intensity of typhoons like this. So, and then this is the actual trial, our measurement. This is also becoming weak typhoons, but we captured from different angles, slightly different angles. From this, we can make the 3D model of the clouds like this. So the already center hole was disappeared, but we can see the very clear rain band, the spirals. And this is another example. We can see the clear hole from above. and we can see the very detailed structures looking at the specific area by the target pointing the operation like this. So we can reproduce the 3D structures of the eyeball. And then all these pictures are taken by the operation based on the day before information about the center of typhoons like this. So this kind of images cannot be available except for the airplane measurement. So, but now our the tiny toy satellites can make this kind of measurement. This is impossible with geostationary satellite because it looks at fixed angles. So this is a daily variation of the center structure of typhoons, and we can draw the cross section of the vertical structure of typhoons like this. So we can track the development of typhoons using these structures. And as I introduced in the Venus exploration, so we want to make use of the new sensors, event vision sensors, which produce the deviations from the former frame. So then we can capture the discharges very clearly, and the output of the data amount is very small. So it's very preferable for the measurement by small satellites, which has limited the communication the data. So then here I want to suggest to make the microsatellite together under the international collaborations, and which is very much useful not only for the pure science but also for the disaster mitigation. And size must be around 50 kilogram, and the low Earth orbit, polar or low inclinations too. And the development period is 1 or 2 or 3 years at maximum. And the cost must be $8 million US. It's still very big money for me, but compared to the big satellite, it's only tens of even 100 times cheaper than the big ones. And the possible sensors, the candidates are the event vision sensors, optical spectral imager to know the water vapor distributions, and the microwave receivers, and VLF and thermographies. So all these instruments can be on board one satellite with a weight of 50 kilograms. So this is my dream. Under the international collaboration, we can operate, say, the 24 satellites. If we have 24, we can watch everywhere over the world continuously. So, and if we have 48, the double of 24, then we can watch all places together with the 2 satellites, like this. So then I want to say that only 48 is enough to monitor the world. So I had this idea more than 10 years ago. So at the time, the number of 50 is the quite huge number, but it's quite small number compared to the SpaceX. So we can make all the 50 satellites with the budget of the one big satellite. So then let's get together. So we can consider this possibility seriously. Thank you very much.
Okay, thank you. You always have wonderful ideas. Too wonderful. And so the question to you is that you have this idea 15 years ago, you say, 15 years ago. But now that today, if you want to have the same thing, can you do it with a small satellite like a CubeSat? And that will be even cheaper.
Yeah. So this is one of the possibility. But according to my experience, the CubeSat success rate of CubeSat is quite small at this moment. Still, it's cheap. So therefore, we can combine both the CubeSat and the micros. So then we can maximize the output. Yes.
Yeah. Please. Yeah.
Yeah. Just one small question, Yuki. 50 satellites at any given moment, but for how many years? You will need to resupply, because nano and microsatellites, they don't live long, as we know.
Yes, my idea is to replace every 5 years. Because if the old satellite exists a long period in one orbit, then occupy the area, then which may cause the collision each other. So therefore, my idea is to avoid the drop down to the atmosphere after 5 years work. Then we can launch the better ones 5 years later.
Okay, good. If I were your funding agency, I would say, Yukihiro, come back with half the price.
Yeah, this is, if we make the 24 or 48, the price cost must be the half.
Yes,
Yeah.
yes, that's very true. You don't times 50. Okay, Professor Yan Liao.
Yes, I have a question. I have a question. Before asking a question, I think maybe the 50 satellites can live longer than 5 years. Okay. My question is about the statement, Yuki. You said that the prediction accuracy is reduced about the type 4. I wonder what type of parameter are you referring to? Intensity, rainfall, track, or like wind speed?
So I'm pointing out the accuracy of intensity. The track accuracy is improving every year, but the intensity accuracy is becoming worse. So I think the measurement of the center pressure itself has a big ambiguity at this moment. So therefore, we don't know it's improved or not at this moment. So then my idea is not a prediction, but the center pressure measurement itself. So then that could lead the improvement of the accuracy. That's the point.
Okay, thank you.
Yeah, I think that usually the lifetime of a satellite like this would be 3 or 5 years anyway, right? And
Yes,
the instrument would decay and so on.
Yes.
I think that's wonderful. We'll talk about that more later, some other patients. So the next talk will be given by Professor Yuan Liu. And, his title is The Impact of Lightning Activity Due to Urbanization. How type-based growth enhance the cloud-to-ground lightning. Yes, please.
So that I don't occupy too much time. Okay, so hello everyone. What I'm going to talk is about, the title is a little bit shortened, so easier to understand the main concern. I currently reside in northern Taiwan, although I originally come from the south. Over 5 decades ago, I vividly recall observing frequently afternoon thunderstorms, which sparkled my early curiosity about lightning phenomena. And but nowadays, such thunderstorms seem far less common. I wonder whether this change is simply due to my relocation to a different climate zone within Taiwan, or if it reflects border shifts in our climate system that have reduced the frequency of convective storms. So motivated by the enduring childhood curiosity, I was pleased to support a lab member in pursuing research on lightning, an area that naturally connects with my core academic focus in remote sensing GIS. So what I'm going to share with you is about intersection. And as shown in the slide, urbanization effects on lightning, and using the Taipei as a case study. So this presentation, the content is many from 3 studies, 3 papers, and they are about the urbanization and the cloud-to-ground lightning, and they are published in the literature. And this page shows a little bit about the research motivation as well and the context in Taiwan. Urbanization in Taipei and lightning context, you can see from the left-hand side of the slide, you see that the population of Taipei is increased much from year 1965 to 2010, and the mean surface temperature is also increased much during that time frame, and we can also see that the urban heat island intensity was intensified during that time frame, and also the aerosol pollutions was increased. And this shows the data and the methodology. The data collected is shown in this page. You see that we mainly collect the data. Well, I should say that we do not collect the data, but the data are from the lightning data are from Taipower, and we also collect other parameters that are of concern, like PM10, SO2, NOx, and ozone, and also other data like convective condensation level, aerosol optical depth, etc. Also surface temperature, population in use, and lens imagery. And from the 3 figures, we see that the population of Taipei and the new Taipei city, that are the 2 major cities in northern Taiwan, the population is increased with time. And the next figure shows the built-up area increase with time for that time frame of a study. And also the last shows the daily mean temperature is also increased with time. And on the right side, that it shows the 7 lightning detection system. This system, I think, it's quite. It's the data we use are from the first 2 generation of the lightning detection system. Now, Taipower company has installed new lightning detection system, and based on the data we collect, we have observed the significant enhancement of the Taipei, as addressed below. The negative fresh density enhanced by about 64% and positive by 48%. Overall average by 56%, and this can be shown in the slide. And this shows another finding in enhancement of cloud-to-ground lightning activity. We see from the right side the correlation, like with the PM10 is a positive correlated, and with the pollutant like SO2 also that's a positive correlated. And this shows the lightning hourly variation urban effects on cloud-to-ground lightning are more obvious in the afternoon than evening hours. And this shows another key finding the role of surface pollutant. Here, the first slide shows the cloud station level. That's a slightly negative correlation. And for other pollutants, you see the positive correlation, like with the, this is SO2, and this is aerosol optical depth, and this one shows the aerosol optical depth. And this shows another result. This is about the scattered product PM10, SO2, NOx, and ozone concentrations versus cloud to ground lightning. So they show a positive correlation. And on the right side, it shows the variation of a daily average concentration of NOx and ozone with the lightning days. And this shows the land use land cover change and the thermal versus aerosol hypothesis. So here we can see that it's the evidence of urbanization is addressed here. So the like population growth by 2.5 times in the study period, and about the thermal hypothesis. So it's clear agreement found between the spatial distribution of cloud to ground flashes and the apparent surface temperature, and areas with higher cloud to ground flash density cross match regions of highest surface temperature. And the urban heat island effect combined with the sea breeze channel through river valleys drive its convective overturning enhanced lightning. And these results are shown on the right in the figures on the right side. And this one shows the scatter plot between the number of cloud to ground phases and the PM10 concentrations. And on the right side shows the again the flashes with the SO2 concentration. We see that the positive correlation for both. So this shows the conclusions. Consistent enhancement. All studies confirm a significant enhancement of cloud to ground lightning activity, both negative and positive flashes over and downwind of Taipei due to urbanization. And the dual frequency, both thermal and aerosol pollutant hypotheses are crucial in explaining the observed lightning enhancement over urban areas like Taipei. And then specific pollutant roles, as shown in earlier figure or slides, we show that the SO2 generally shows a stronger correlation with the cloud to ground lightning compared to PM10. And also lightning itself is a source of NOx and O3 ozone enhancement in the lower troposphere, particularly on lightning active days. And also other issues like temporal patterns and complex interactions implementations addressed here. And this page is, we suggest some of their future works, like a quantitative attribution modeling. We can apply high resolution models like a Wolf chemistry model to quantify urban heat island versus aerosol effects, and the run sensitivity experience with the variant they use and cover pollutant concentrations. I think for this type of future works, I try to link the lightning with the phenomenon that can be monitored by remote sensing or by models. And the second is the multiple city comparative studies, like Taipei, Seoul, Bangkok, Jakarta, or India. I think lightning activities is very active in India. And in earlier presentation, we see that the death number in India increased much especially after year 2007 also. That increase actually is very amazing, big and fast trend. So it's worth to understand the lightning and even predicted lightning activities better in order to protect the lives of the citizens. And the long-term trend analysis, also public health infrastructure impact, and the last is the vertical profiling campaigns. Okay, this is a brief of the 3 studies that we presented in the literature, and they represent the works that we have conducted earlier, but they are kind of case studies and not so complicated. It would be nice to see this type of studies, because they can be easily understood, and the citizens can better inform the threat of lightning. Okay, this concludes my talk. Thank you.
Maybe I ask Professor Krishna, do you have any comment or questions on this presentation? Yes.
Thank you, Professor, for an excellent presentation. When you discussed the correlation between lightning and atmospheric optical depth, AOD, you said there was a linear relationship, if I recall. I wonder if you found the boomerang effect when you have too much pollution, the AOD increases too much, then there's actually a decrease in lightning. We have some works on that following research in Brazil. When you have forest fires, for example, and you have too much aerosols in the air, smoke pollution, then lightning actually decreases. So it starts to increase and then decreases.
Okay, I think you have conducted more detailed investigation than the studies. The results are shown in the presented 3 papers. So it is possible that the impact or the correlation may vary like the way you describe. And the data that we use, I think they are they are limited. You see that from the slide, we have limited number of data used in this study. And you see that this, at that time, it was not the lightning detect system in Taiwan. Even our Taiwan Central Weather Bureau did not have lightning detection system. And at that time, I found that the Taipower has the detection system. So, but at that time, there were only 7 stations. And you see, not long after I used the data, the Taipower company installed new lightning detection system. Mainly, I believe, mainly because the system was very old at that time. So I think nowadays we understand the lightning physics better than before, and we have not Taiwan. I think globally speaking, even in like India, install more detection systems. So I think it certainly is a better timing to conduct further and deeper studies, as you said, and then that type of outcomes findings will be even more helpful. Thank you for your
Thank you very much. Thank you very much.
Yeah, thank you. Other questions? Other questions for Professor Liu?
I don't see that, I think that we'll continue. The next.
By the way, Professor,
yeah, go ahead.
Allow me to state one more thing. I think at the time I conducted that research about lightning, in the class I took the students to visit the Thai Power facility. The facility is very good in my memory, but I haven't visited the facility for, I think, at least 15 to 20 years. But if anyone who is interested in lightning, I think the facility of Thai Power, that would be a very nice place to visit. The first time I walked in the facility, I was shocked by the room, the facility. Even though it's like a deep space, very huge. A whole aircraft can be brought in to the facility for conducting lightning experiment. I was very impressed with the facility. So it's nice. Okay, Professor, yep, that's my additional statement. Thank you.
We come to the next talk to be given by Professor Masashi Kamagawa. Professor Kamagawa, are you ready?
Okay, I'm ready. Just a moment, please. I want to share the screen. Okay, so my talk is not scientific results so far. So we developed one of the CubeSat, which can detect lightning from the Earth ground. So CubeSat is very small, but so we can detect the lots of lightning from the space. The satellite name is Prelude. This Prelude will be launched in this physical year 2025. This is the image of this CubeSat. Then I believe everyone knows that. So if we want to detect the lightning specks, so it is better to use the electric field measurement. This is one of the example. So this is the French satellite Demeters. So they have the 4 booms of the electric field measurement and 1 boom of the 3 components of the magnetic field measurement. And also they have the plasma measurement of its boom. Then this is one of the example of the one orbit during nighttime and the spectrum data. The upper panel is electric field, the lower panel magnetic field. So this is the spectrum data. So as you can see that, so this is the same period observation, but apparently, so the electric field measurement much more sensitive. So this vertical flash is corresponding to the one of the strokes. So in the magnetic field measurement, so we can not see the many pulse of this one. So it means that it is better to use the electric field measurement of the high sensitive lightning detections. So in order to observe the lightning activities from the satellites, so we developed the wide 6U size CubeSat, so-called the Prelude. This is schematics of the Prelude. So this is the wide 6U satellites. The half of them of the satellite is for the mission part, including in the probes, 2 probes and 2 booms. The 2 booms can be extended like this one. So one of the boom has a 1.5 extension boom like here. The top of the boom is embedded in the probes here. So we can observe the electric field between the 2 probes. This is the deployment. Then the 3 features of the Prelude is as follows. One is we can observe the lightning with high sensitive electric field intensity, and also we can observe the plasma measurement. So this is the one of the example of the time series of the electric field measurement observed by the Demeter satellite. So we expected the quite similar signals from our satellite because our boom is totally more than 3 meters between the probes. And also, important things is if we want to put the probe should be very small. So we can design this kind of the probe. In the probe size is only 3. It's very, very small size in so with the interface. And also, and so if you develop this kind of satellite, maybe this kind of satellite is maybe good for the electromagnetic observation for the Earth. In particular, this is a CubeSat, so it is easy to construct of the satellite because it's very cheap and it's very small. So it means that it is easy to construct the satellite constellation. It means that we can deploy the new type of the observation of the geomagnetic science. Then, so our measurement approach is quite simple. This is a well-known measurement. So we observe the two potential difference, and so this is a double probe method. So we can observe the potential at the sensor A and the sensor B. Then so we can calculate the electric field divided by the two lengths. So this is one of the our measurement system, and also this kind of probe can be applicable for the Langmuir probe. It means so we can also observe the plasma parameter. So it means that we can apply this kind of probes observe the Langmuir curve, IV curve, like this kind of curve. So we can switch of this kind of the potential measurement. It means the electric field measurement and the plasma measurement. So we can observe both parameters. So sensor probe is like here. This is the hybrid sensors. So the sensor is like here. This is spherical probes covered by the carbons. Then so we have the pre-amplifier inside this spherical probes. Then we send the polarization current to observe the electric field and so Langmuir curve. So we can observe in the DC electric field and AC electric field, and also electron density and electron temperature. Of course, we can observe the ion density and ion temperature from the Langmuir curve. And so this is a new technology for the CubeSat measurement of the electric field. So usually the relatively large satellite, it is not so considered this kind of the system, but CubeSat is very affected by the Langmuir measurement. So, for example, during Langmuir measurement, a lot of the electrons absorbed in the satellite. It means the satellite absorbs a lot of electrons inside. It means the floating potential is disturbed. It means so it is not so good for the measurement of the Langmuir curve. So it means we should emit of the electron density to keep the stable floating potential of the satellite. So this is the schematics of the circuit. So we have the carbon nanotube here. So we have the grid in the grid here. So we inject in the potential difference here. So electrons emitted from the carbon nanotube. Then this carbon nanotube accelerated between the two capacitance. Then finally electron emitted from here. So we use this idea to then we install this kind of the system to emit the electron to keep the satellite potential. Then also, so we have to develop the very, very small boom deployment here. So this is the schematics like here. This is the extension and the photograph like here. We have the probe here. This is the system. So if you extend it like here, this is a ground-based experiment. So if you release and booms, so boom can be deployed like here. So we have the two probes like this kind of the booms. Then the measurement is we have the two modes. One is the spectral mode, the continuous spectral mode. In our current situation is 1 Hertz. The data regularly, and so also we can access in the burst mode. So if we want to data, if we want the waveform data as we like, so we can send a command to the satellite, so we can pick up the raw data. Of course, raw data is very huge amount, so we cannot send all of them. But so if you send the command, so you can get the waveform data as we like. The sampling rate is 40 kilohertz. And in addition, so we have a DC electric field measurement, and so we have the plasma electron density and temperature measurement. So as I mentioned, so electric field measurement and plasma measurement is a switch measurement, alternative measurement. So it means here our plasma measurement is a 5-second sampling. And so we applied also ground station, a cloud ground station. It means so we use in the global the ground lot of the ground station. Of course, if we have a lot of money, so we can use a lot of the ground station. But so if we have the a small amount, so we can use a 2 or 3 or ground station. Then so we have the specific and program, so we can remote control all of the station. It means so we can get lots of data from the global ground stations. In this prelude, we employ the S-band communication, but so the if you need, if you can replace in the S-band by the X-band in this satellite. So far, our satellite is the stage of the FM development, but so we can try to do some of the laboratory experiment. This is a plasma chamber experiment. So we put the probes and the probes, 2 probes. This is not carbon covered. So if you apply the Langevin curve measurement, this is a Langevin curve. This is a carbon covered. This is not carbon covered in the large hysteresis. And so we can observe, try to the electric field measurement. So we can clearly observe the signal from the generators. So it means that our system works well. So we can expect the plasma measurement and field measurement both in the space. So in this presentation, I show the capable of the lightning measurement, but so our main purpose of this satellite is different. This main purpose is ionospheric earthquake precursor verifications. So because Demeter satellite in the produce a very statistical good result of the ionospheric precursors. This ionospheric precursor is related to the lightning spheric signal. For example, so our expected ionospheric precursor is occurred in the lower part of the ionosphere. So increasing of the electron density in the D regions. Once this kind of the electron density D region occurred, this kind of the spherics absorbed of the intensity, and so we can observe a small intensity of the lightning signal. Then we can understand this existence of this kind of the precursor. So purpose of this satellite is observe the spherics, but so the main target is this kind of the precursor verifications. So this is the conclusion. So we developed of the design in the wide 6U previous satellite. So this is good for the ionospheric electromagnetic phenomena. Then in this prediction mission is the verification of the ionospheric precursor. But so various missions such as the lightning and the space weather, it can be applicable. Then this mission unit very, very small and simple interface, and so install the other satellite easily. And so our satellite will be launched during the physical year of the 2025 of the JAXA's fourth Innovative Satellite Technology Demonstration Program. That's all. Thank you for your attention.
It's to be launched this year, right?
Yes, this year.
Why is it called?
A few months.
Yeah. Okay. What's it called? It's a 6U CubeSat, is it?
I cannot hear that.
I mean, the name is a W6U. Is it because it's a 6U CubeSat?
And wide 6U, relatively wide size of the 6U size.
Okay. And may I ask? You don't have to answer. How much is the cost for the mission?
How much is the cost? I did not calculate the total cost of the amount. It's not so cheap. It's not so cheap. I think.
How about bus? Satellite bus?
How much?
Bus.
But how much? Bus?
The satellite itself. The satellite bus cost.
Satellite bus cost is
Japanese
yen is 3,000 yen.
3,000. That's reasonable. How much is then? I mean, in $200,000. $200,000.
Yeah.
The full bus.
The full bus is 3,000. Yeah.
$200,000.
Yeah. Like this one. Yeah.
For 6 years. Okay. Other questions from the audience? I mean, this is very technical because all instrumentation, obviously, Professor Gama is an extremely good instrumentalist. And if not, I think it would go to the next talk is to begin by Professor Tiger Liu. The title is Earthquake and Lightning. For some reason. Okay. So I think I'm going to say something maybe everybody get very skeptical because earthquake and the lightning. The reason why I'm got this problem actually was this, in the year. Do I have the microphone on? Yeah. Yes. No. Okay. And actually, this work has been done on 2015. By then, because in the very beginning, we saw the lightning actually hitting the 7.4 of the Chichen earthquake. And you can see on the this is a red dot. I'm going to coming back to this one also. And also along the fall, we see a tremendous anomaly of the magnetic field. So we start to wonder, see if we can be able to see the because both are related to the electric field. So we work on that. Actually, I just overhear that one talk about if the lightning should affect the atmosphere. So I'm going to show you atmosphere. So the content I'm going to talk, so I'm going to introduce a little bit about the introduction, then following with this GPS TEC anomaly and earthquakes, and the geomagnetic fluctuation during the Chichen earthquake. And then finally, I'm coming to the main topic of the magnitude 5 earthquake in Taiwan. That's related to the earthquake. So I come to conclusion. The GPS, I think everybody knows that. The advantage of that one is free, because the transmitter, the signal down to the receiver, so we can calculate the TEC. And because one GPS will be able to receive more than up to 8 to 10 receiver. In nowadays, it's for GNSS receiver even better, because we have a GNSS GLONASS, we have a GPS GLONASS and Galileo together with the MEDO. So we can see two-dimensionally all the information that will become true. So whatever the key point, we use a GPS TEC to do that. So this one example, observe over the Yangmingshan So 24 hours, and each curve stands for different the signal from the different directions. So that's meaning spatial resolution. We can see that. This is one of the example. We're using the 13 GPS receiver, and we pick up the overhead in the computer with the overhead. We can see the GPS actually varying by that one. The upper thin line and lower thin line was built. Upper bound and lower bound was computed every hour with 15 days before. So we calculate the median value together with this so-called median base. So we add the upper quartile, lower quartile, and times the quartile difference with 1.5. And we can, so whatever we declare that's meaning, for example, this decrease anomaly. And so this 1 day before and then 3 days before, and you see the density actually drop very, very low. So we also look, since we have the spatial, the data simultaneous overhead. So this is a vertical, is latitude, and this is a local time. So this is an earthquake day, is over here. It's before 1 day before, 2 days, 3 days before, as you point out over here. You can see the EIA crust actually move toward equator wall. And then I will show you that later on. If we have the EIA move to the equator wall, that's meaning stand for electric field actually pointing to the west. And this happened to the 3 days before, 4 days before. So EIA actually move over there. And actually we also built up one way to compute EIA crust. So we can estimate the electric field. What is the electric field? Okay, this is the latest progress. So actually it's not a surprise that actually we looked at the data. By then I didn't know that we have 12 days and 15 days also decrease. And on your right, and that's what we just showed you on the day 1, 1 day before, 3 days before, 4 days before. This is a local time. This is 12 o'clock, 2 p.m., 4 p.m. So this is subtracted for this with this medium, 15 days median. And this is with resolution of I think it's 1 degree or something like that. And if you subtract observation to by the median, so you can see that the epicenter, bullseye. Everything is not only decrease over the epicenter, actually it's spatially specifically over the epicenter. I actually removed some of that with a global because this is the paper under construction, so I didn't show you that. But I told you specifically over the the epicenter of the GGS wave. What I just mentioned, because every day you have an eastward electric field and will cross product with the northward, the magnetic field. So you have raised the plasma fountain, go to the pile up on the of the equator side. For Taiwan, that's will be exactly the EI region. So this is the maximum. So if we have a map with westward electric field, so the pumping was not go so high. We're going a little bit close to the equator wall. So that's exactly what we saw that. So by using this one, we can calculate the electric field. This is one of I didn't know we have an in-situ measurement. This is a DMSP satellite, satellite, F13, and so they go through all the data. They measure the electron density. They also measure the velocity. So we can derive the velocity by using dynamo series process. So that with the ion velocity cross product with the Earth's magnetic field. On your top panel, this is the day 3, day 4. So you can see the reference, that's a 0 line. So density actually decrease. So this is well agreed with the GPRGs. And again, we see the something over the 10 to 15 days before. So now you can see much more intense. They drop down all the way. So actually, we look at the GPR-based GPR-TEC. In fact, over that one, so also over there is a decreased TEC, is very prominent. So we calculate that one, the eastward electric field. And then we can see that 14 days, 10 to 15 days before, that's actually 10 to the westward. That's meaning about the 51.5 millivolt per meter. Similarly, over here, the 3 days to 4 days also westward. So whenever westward, in EI epicenter, your density is going to be decreased. So I will show you the EI crust. You can see the EI crust completely move to the equator wall for both the code GIMTs, also the JPLTIC, so you can see all the detail. Actually, I verified that one by using stone cases. Actually, this is a positive stone. So the positive stone, there's the increase. Your electric field actually point to the east. Okay, so we can cross product by using the earthquake follow there. Okay, electric field is important. So this is the only base I need there. This is the other. So we look at this. If this happen all the time, if the true sciences should be occur all the time, can be repeatable. So we follow that one. The earthquake will pick up 20 magnitude 6.0 earthquake, and during this 2 years and more, and you can see the 0 day to 5 days before, similar to the previous one. You can see the negative anomaly has been increased about almost 40%. Usually only the 10% or the 15%. So this is again confirmed. This is science because repeatable for the related earthquake. And the other one is also the trigger my why I'm doing that, because one of my colleagues worked on the Chenglin fall, which is the magnetometer over here and here. This is the Chenglin right over here. This is of the the so-called earthquake, the fall zone area. So what I did actually I showed you this is a daily variation. You can see the daily variation is about the 30 to 20 nanotesla. And I showed you we subtracted this one to this one, so we can obtain before the earthquake and keep doing like that. Actually, the triangular doesn't mean that we place the magnetometer, because this data is ridiculous, because the magnetometer keep mentioning malfunction. So look at this one. This is about 150 nanotesla. So this is much stronger than the daily variation, and that is occur all the time until this is the other earthquakes over Jiayi. This is the other ones, the TW site, and once the earthquake occurred, it shuts it. Okay, completely go back to normal. If this is a mechanical problem, it will not stop, but it stopped. That's meaning the sources of the current or electric field has been shut up. And then we also take the other triangular site, and this is subtracted the reference site. And this data, you can see the whole bunch. That's crazy about the 100 nanotesla. So somehow during around the fall, before the earthquake, it issued some kind of electric field. So this electric field induced the lightning owner, affected the owner. So I go back to look at the data. That's during the Chichi earthquake. Now we pick up the 308. Okay, that's big enough. Magnitude 5.0. And the cross one stand for the ocean, the earthquake. This is so-called the land earthquake. And the ocean earthquake, actually, later on you will see that one is not sensitive to the earthquake, because everything will be on the lake. I showed you that now. This is 3 days before. This is 4 days before. You can see along the fall. It's crazy. There's lots of lightning completely there. Okay. So, okay, this could be happened during the geographic location because of mountain. Now, you are on. Okay, I will show you. And I put the square that one. You can see that before the earthquake, the intense lightning. Again, the other one, 10 to 15 days. Again, lots of lightning activity. So this is only time series. How about we will see more detail. So what I did actually, I picked up the magnitude 6, night earthquake, to put over there. So what I did actually is take the earthquake and pick up the boundary over the epicenter. So count on the right and with high power lightning data. So count if there's count how many days in each day, how many lightning landing, CG lightning, and you can see that one. This is before the earthquake. Just purely by eyeball, you can see that this is before the earthquake. We have much more frequent, lightning activity. So what I did actually today, 1 days before, 1 day before, and 1 day after, 2 days before and 2 days after. So complete all the way cumulative, the day. And I mark over here day to the earthquake, and you can see that one. So and I also added up and put the number of the earthquake, so you can see the number of days total is 9. So around the 5 days they reached up to day, and here 18 days, almost 90% of the earthquake. That's meaning before the earthquake, it's more frequent than after the earthquake. So that's meaning something before the earthquake is very, very real. Okay, then we'll come back. So let's focus on the number 18 days. So I pick up the sea earthquake, and this is the earthquake magnitude, and also calculate the number of the earthquake, and to the number of which is so-called the before and more frequent. And you can see that for sea earthquake you don't see anything. But however, you look at the number of magnitude earthquake, and this is the day before the to the earthquake than before. On 18 days, stronger earthquake, you have a higher number and of the PEIA. Okay, again, this has been shown in previous with the 6 earthquake, magnitude 6. So here's and whenever the earthquake become smaller, then the signature become bigger. Okay, that's meaning stronger earthquake has a better chance to show the obtainers with so-called much more odds ratio. We'll come back here. On the panel 8, that's a magnitude with a depth. The solid circle stands for earthquake before have yield more it has a frequent the sort of lightning activity, and this again on this 18 cumulative days. So the shallow earthquake, if we calculate the odds for the magnitude without considering the magnitude, you can see around the less than 20 kilometer. This red line, the odds equal to 3. Everybody, if you go get gamble, somebody say, I have a 3 times stronger better chances to win you. So don't ever gamble with me, because that's a very, very significant. That's actually it's just sin level is more like a 0.005 for the p-value. This is the odds for the again for the earthquake magnitude. So earthquake magnitude, I think, is over the somehow the magnitude around the 6 something, and this has become very, very confident. So you can see odds ratio is also proportional to the earthquake magnitude. Okay, is this happen everywhere inside my observation? No, actually we subdivide the landing because we know the location. So we added them together. This is before the earthquake, how frequent that the earthquake is for the the earthquake, and compute that one. And this is the magnitude 6.0. This is greater than 5.5, 5.0. Certainly, if you look at that stronger earthquake, you have better chance, better count. And then you look at this after. So what I did this divide by less. So that meaning, so we put over here. So the circle, that's meaning the very frequent. And you can see that one, the proportional over the epicenter, we superimpose all the the earthquake over the land earthquake. So now, that's meaning around the epicenter, the lightning activity is much more frequent. Okay, so this comes from my conclusion. A larger earthquake, the greater proportion within the shorter cumulative date. And larger earthquake has a largest significant area around the epicenter. So you can see the last one, the significant area is bigger. The larger earthquake, the shallow earthquake, has a better chances to experience the lightning occurrences. The other one is a larger shallow, the land earthquake inhibit great energy because the deformation and the charged electric field come up, and which modify the electromagnetic environment, and in turn induce lightning activity during the earthquake operation period. In short, statistical significant evidence shows the more lightning activity occur around the epicenter few days before the larger shallow land earthquake, than the other times. I also like to address something more. In fact, we're doing the same thing with the TIMM. So I'm looking forward to seeing the Professor Takahashi's satellite if they detect the lightning. I think even detected from space, the result is similar. Actually, I'm also doing with the Woolen result also very good. You the similar tendency. This concludes my talk. Thank you for your attention.
Okay, thank you. What's the deal? Other questions? Any questions on this interesting relation? Yes, please. Yeah.
So besides the earthquake, so I want to know the if you can see the effect of the individual lightning on ionosphere. The 1-to-1 transformer. Have you seen that?
I'm actually using the CIMM for individual lightning, individual earthquake.
No. I mean the one lightning and the effect on the ionosphere.
I don't.
Oh, have you seen that? Have you examined that? No? Oh, well, I'm very much interested in that because the lightning may modulate.
I'm sorry. The answer is yes. I have a student paper to work on that. What I got is if you over here the lightning in the thunderstorm, and there is the lightning, and for our ionosome, we will first come up with this very intense ES occur, and then we will see the very strong, the plasma depletion for the F region. So in that case, actually, there's lots of the energy charged particle precipitated from the space.
No. I mean the effect of the lightning on ionosphere, not the effect. The lightning radio waves can penetrate only the lower part of the ionosphere, not to F regions. The E region at the maximum.
The whatever your whatever may be right, but what I would like to address, because the lightning they will activate ELF or ULF wave. So the wave going into the ionosphere follow the trap to the tube. They will interact with the ionosphere. They will precipitate a shower.
Yes, I know. Yes.
Yeah. That's so it's going up.
No. I'm asking the direct effect by the radio waves emitted from the lightning.
I haven't seen that.
Oh, have you examined that? Or
not yet?
Not yet. Okay.
Yeah, we can do that.
Okay. Thank you.
Okay, good. So we are waiting. Finally, we have the last talk. Professor Yai, the talk is a surprise on other planets. I must say that because of time difference, and then also sometimes you have a special requirement for your timing, so we have not been able to put all the talks, 11 talks, into one single block. Yeah. So on one hand, this talk could be partly having to do with the planets too, right? But anyway, here he is. Yeah, please.
Okay. I hope you hear me well. Let me try and share my screen with you guys. All right. Thank you very much. So for those of you who don't know me, my name is Yair. I'm at Reichman University, and I work on lightning on Earth and other planets, and on transient luminous events. And some of my very best friends and colleagues are here with me today. So what I will describe is a kind of a unique and maybe outstanding new research we've been attempting to do. And it's not a new one, actually. It started in 2009, actually. And I will talk about sprites in other planetary atmospheres and beyond. So this is kind of an AI perception of how sprites would appear on the planet Jupiter. So you can see how beautiful they may look, if indeed they exist, and we believe they do exist. So when we look at planetary lightning, there are obvious fingerprints that we look for, especially if we look from space and we discuss planetary or exoplanetary lightning, as Philip and others have mentioned. We can see them directly in the optical range, and we of course remotely send them in the electromagnetic range, as was described. But we can send them indirectly if we observe transient luminous events higher up in the mesosphere or just below the ionosphere of that planet. And of course, we can search for chemical fingerprints, both of the lightning itself in the deep atmosphere or of the lightning-induced sprites in the upper atmosphere. So there is a distinct rationale for looking for sprites on other planets. And in response to this question, why should we study planetary sprites to begin with? I would offer the following rationale. Okay, so lightning is essential, as we know, for the production of chemical reactions that may bring about the production of pre-biological compounds. Like on Earth, you know, the Urey-Miller experiment. Quite often, as in Earth atmosphere, and as we've heard today from Georg and Philip, lightning can be produced deep in the atmosphere, actually below the visible topmost clouds. So very few photons, if any, can escape into the orbiting spacecraft or reach a ground-based telescope, as in the Venus case. So we may not be able to see lightning directly optically, although we may remotely sense them in the electromagnetic range. But if, on the other hand, we have sprites, then they can be easily observed by an orbiting spacecraft if it has the right camera and the right filters and knows where to point. So this is the rationale. I mean, we are looking for planetary sprites as an indication of the existence of planetary lightning, which are important for pre-biological chemistry. So let me just remind you, I'm sure most of you know this already, that sprites in Earth atmosphere are believed to be produced by the quasi-electrostatic mechanism, first formulated by Victor Pasco decades ago. Usually, I think more than 95% of observed sprites are generated by strong positive cloud-to-ground strokes, which rearrange the charge within the thunderstorm such that there is a short, very short-lived enhanced electric field above the thunderstorm, such that it surpasses the local breakdown pressure, which can amount to very few volts per meter high in the mesosphere. And that would generate acceleration of electrons that can impinge on neutral molecules and emit excited nitrogen, mostly light that can be seen from above. So when we discuss this QE mechanism, the basic formulation requires you to assume something on the properties of the atmosphere, and then something about the properties of the thunderstorms and the charge. So we did some theoretical studies in 2010 and published them in JGR, and we showed that potentially, based on the existing knowledge at the time of thunderstorm structures in Venus and in Jupiter, we can see that for a basic configuration with different amounts of charge, you can see the different colors, 100 coulombs, 250, 500 coulombs, and the location is deep in the atmosphere. Where, at what altitude would you expect to get the breakdown above the clouds? And in Jupiter, notice that the ionosphere is 300 kilometers above the 1 bar level. The clouds are approximately 300 kilometers below, so they are located at 5 bars. I'll talk about it in a minute, but the prediction was that sprites in Jupiter should appear 260 kilometers above the 1 bar level, and that's just below the ionosphere. And in Venus, so we've heard 2 talks today about Venus. If there are any lightning there, then sprites would appear higher up above the clouds, but we're not sure that they exist at all. So following up on this rationale of the potential existence of sprites on other planets, we asked, okay, so how will they look? What wavelength will the emissions be, the excited emissions? And so we collaborated with the group of Ute Ebert from Eindhoven, led by Sander Niedam and Eddie van Waldhuizen. And we did, with my PhD student at the time, Daria Dubrovin, actual experiments in what we call lightning in a bottle or sprite in a bottle concept, first developed by Earl Williams back in the 1990s, I believe, or early 2000s. But anyway, they have this uniquely very high-speed camera that can look with a resolution of 1 nanosecond on the development of streamers based on different atmospheric compositions. So we did helium, hydrogen for Jupiter, and CO2 and N2 for Venus. And so when we look at this at a very high speed, this is how streamers look like. Of course, this is for Venus, and this is for Jupiter. Excited hydrogen, excited CO2 and nitrogen. And this was published in Icarus in 2014. So let me remind you, when we talk about Jupiter, and this talk will focus on that planet, we are postulating the existence of 3 cloud layers where the lightning is supposed to occur deep in the atmosphere, in the H2O, which is a mixed cloud of water, liquid and water ice. At the top, similar to terrestrial cumulonimbus clouds, but much, much larger in size. And the simulated light that is expected, and I think we've seen this before, in Yuki's talk, if you look at lightning and Venus, then you would see it in this wavelength, and in Jupiter, this is the Lyman alpha, will be the dominant line, but also helium lines, and in Venus, CN lines and other lines. So this is for the lightning. And for the thunderstorm itself, where will it be located? Actually, I can go back to my PhD back in the 1990s, and it of course depends where the thunderstorm occurs and what is the relative humidity profile, but we can expect really deep, 30 kilometers deep cumulonimbus type of clouds in Jupiter, located below between 1 bar and 5 bars deep in the atmosphere. And indeed, as Ivana discussed earlier today, lightning do exist in Jupiter. We've known this since 1979. And Juno had added a new dimension to our understanding of what lightning on Jupiter would look like. And a new paper by Heidi Becker from the Juno imaging team showed that there may be a different type of lightning that occurs higher up. Let me remind you, in the ammonia cloud layer here. So this is ammonia ice, actually floating above the deep water clouds. But based on Juno new data, probably we have a different family of lightning that occurs in the what we call shallow lightning and not deep ones. But and this is important because when we will model the QE field above a Jovian thunderstorm, it's essential to know where are the lightning and where are the clouds are located, because that would obviously dictate the formation of the QE field above the lightning. And I was very actually excited to learn 5 years ago already from the Juno team that they observed what they interpreted as an ELF in the Jovian atmosphere. Actually, they've seen 11 transient luminous events located high above the visible cloud layer. So it's even higher than the ammonia layer cloud. So it's in the mesosphere, it's below the ionosphere, actually almost in a height identical to where we predicted that lightning would, that TLEs would occur in Jupiter, 260 kilometers above the 1 bar level, dominated by H2 emission. So I'm not sure if this was luck or good physics, but they saw what they interpreted as ELVs exactly at the predicted altitude that we postulated for a lightning-induced TLE based on a deep water cloud. So if I schematically show you the results and the observations, theoretical predictions, where are the water clouds and where are the ammonia clouds and where are the UVS flashes Juno had detected. So this is how we can kind of postulate the basic for our module, for the model that I will present to you now. By the way, I should comment that ELFs were actually calculated by the Granada group with Paco Godillo Vasquez and Francisco Ferrez-Invernon and Alejandro Luc. So published 2 papers. This is from the latest one in 2018, I believe, that they show how elves would look on Jupiter for a deep discharge from the water cloud, as I said before. So we know that the formation of, or the modeling of the emergence of sprite depends on the shape of the current during the discharge that occurs in the cloud. So Victor Pascoe used, and this is the graphs taken from his 1997 paper, a hyperbolic tangents dependence of the current as a function of time, and he ran his simulation for a plus CG and a minus CG and an intracloud with different time constants, tau, for the decay time of the current within this parent flash. That actually, this dictates, of course, the shape and the duration of the quasi-electrostatic field above the thunderstorm in the mesosphere, which of course is essential to the generation of sprites. And we know from terrestrial observations that lightning is not smooth. So this accounts for a very smooth decay of the current, but we know that current in terrestrial flashes is not smooth, and there are plenty of observations to support this. So there can be piecewise variation of the timescale of microseconds to tens of milliseconds. And actually, this is exactly what Ivana showed earlier this morning based on the Juno results. So what we choose first for a terrestrial cloud is to kind of play with Victor Pascoe's initial profile and to make it a more complex piecewise shape, what we call fits and starts of the discharge. And this is the schematic dependence. And we showed this model to actually predict quite well the existence of what we call long delayed sprites. So this is a case study from last February during the AX3 mission, Axiom Space, where we conducted the Ilan-ES campaign, and the astronaut, Michael Lopez Alegria, was able to capture a sprite just above Indonesia. And you can see this really, really bright cloud illuminated lightning. There's another flash up here. And then there's a huge jellyfish sprite that was delayed almost a full second from the initiation of the lightning, which means there was almost a 1 second long continuing current within that sprite producing positive CG that we were actually able to locate both from ELF data, thanks to Hobara Sensei, and in the VLF data from ENTLN. So we know exactly where the cloud was, what were the meteorological parameters. We have satellite images from Himawari and others. So, and we have a balloon radiosonde data that tells us the vertical dimension. So we know exactly where the charges are, what is the charge moment change, and we can actually mimic the current shape using this model to simulate the duration that it took. And you can see here in the bottom row for different types of discharge, how long after the initiation of the lightning, actually the sprite window or the inception window for sprite opens. So it's not like short duration sprites that are almost immediately after the lightning is detected, within a millisecond or two, they appear. And based on my understanding of the literature, my knowledge, there are very rare events that you can see a sprite delayed by more than 150 milliseconds. And here we have almost a full second of delay, and our model for long delayed using this piecewise varying discharge can actually mimic very well. So where are we going now? Sadly, I don't have yet, well, I do have results for Jupiter, but I hesitate to show them because we didn't quality control them. And it was just the first model run a student did before he went on vacation to India. So when he will be back, I will be able to present much better film results. But we have all that we need. Yes, we have the pressure temperature profiles for Jupiter. We know what the clouds are. We can assume that the lightning within those clouds is similar to terrestrial clouds based on Ivana's data. And so we will simulate the generation of sprites. This is a 3D model. I forgot to say, because in 2010 we used the 1D model. Now we have a 3D model, and we can actually show what shape sprites will be on Jupiter based on our assumptions on the lightning. And then we will move to Saturn, Uranus, and Neptune, as Philip had shown, and Georg. Plenty of lightning there, so should be plenty of sprites there as well. And as we say, to boldly go beyond, like in the Star Trek TV series, to go beyond the solar system and maybe discuss the potential for sprites on exoplanetary atmospheres. We are actually now forming a European-Israeli group with many experts on exoplanetary atmosphere, exoplanetary clouds, and we're trying to merge the knowledge. And Philip, I embrace your proposal to maybe join your team and discuss with your team the potential for looking at exoplanetary lightning. But for now, in the short range, we will discuss hydrogen-based atmosphere in our solar system. So this is where we're going, and I would thank you for your attention. And this is just how maybe someday we will be able to look from a spacecraft on a distant planet and see this wonderful ELF, which was taken during the AX-1 mission. This is above, actually, the Pacific Ocean. Thank you very much.
Okay, thank you. Thank you very much. I can see that Philip wants to ask a question.
Yeah, I think there is a misunderstanding. You have. I said that we cannot detect exoplanetary lightning.
No. I know.
Oh, okay.
I'm asking. As I said at the end of my summary, we're looking at planetary now.
Oh, planetary.
So we want to look at Jupiter, Saturn, Neptune, and beyond.
Fantastic.
So I think this you have the perfect tool for that.
Okay, fine.
Okay. Questions from other people? Questions? I think it's very interesting. I mean, the amazing work. Yeah. Please, Gil.
Yoav, do you have any plans for, I don't know, a student for going through JunoCam images, Cassini images, to actually look for these things also?
Well, we didn't actually thought of that, but I might have. I have two master students. One is doing the Jupiter modeling. The others should go to other planets. But if there is a way to look at images, wow, that's a brilliant idea. I didn't think of this repository because she's an expert. She's an expert on machine learning, so maybe she can train on the data set and look for unique signatures. But let me talk to you about this offline. About this. Thank you.
Yeah, Philip.
Georg, that's very interesting. Are you talking about the database of images from the Cassini ISS?
Yes, for example. That would be just one example.
Because I never thought about it, but it just reminds me that there is a student, not of mine, but at Observatoire de Paris from a colleague, who developed a machine learning code to detect the cosmic ray impacts in the ISS images. And so he classified millions of signatures in the images. And I should ask him, is there anything he rejects that could be lightning, that probably has a different shape in the images?
Yeah, that would be interesting.
Yeah, I'll definitely ask. That's a good idea.
Yeah, brilliant idea.
Okay, very good. So I mean, this discussion is useful. Other questions? If not, I think that we have long day. I mean, even though we start at 1 o'clock in Taiwan time, now it's 6 o'clock now. So 5 hours. I thank you very much for your patience and your endurance, in fact, and all your participation. For discussion, concluding discussion, I want to make a suggestion because next year, the AOGS meeting will be held in Fukuoka, right? Fukuoka. So my proposal is that Yukihiro, you submit a proposal on planetary lightning. Yeah, and you cannot refuse, right?
Yeah. So my standpoint is the former president of JPGU. And the next year, JPGU has a joint meeting with AGU.
Right. I mean, actually, I'm thinking of having a joint session with the EGU.
AGU, yes.
EGU.
Not session. Joint meeting.
Joint meeting.
Whole joint meeting.
But then you need to have session, right? I think the one session would be on planetary lightning. Is it okay?
So
and I would because you're in Japan, I think you should. Okay,
Yuki, I'm willing to help you organize that, like we did before at AGU. Remember, I think more than 10 years ago. I should say that at EGU next year, the call is not published yet, but at EGU 2026 in Vienna, one of the topics that is already included in the session description is planetary lightning. So I urge all those present here to submit. I know last year we had several talks, planetary lightning talks, maybe 2 or 3. One was exoplanetary lightning talk, just a theoretical discussion. But I think, Philip, what you described today is spot on for the community of planetary lightning researchers at EGU.
I would be happy to report analysis of this data, of course.
Sure, because the lawful people, they show up every time for the EGU session.
Because there are very nice results on Earth lightning, of course.
Yes, okay.
Yes, of course.
Now you open the new window.
You're talking about EGU or talking about AOGS? I mean, for AOGS, I think partly would be also to broaden the participation from the Asian community too, right? Yeah, I mean, that is the one of the purpose. Yeah. Okay, we will talk about that. I mean, the story. If Yuki is going to propose, you all will be invited. Yeah. Okay, you want to say something, Yuki? I mean, because for you that we have this workshop. Yeah.
So I'm very much happy to hear so many big variation of the lightning researches. So I want to promote the next action for the project. So not only the satellite, but also the ground measurement as well.
Correct.
So we want to explore the possibility of the planetary and Earth lightning studies. So involving the whole world.
I mean, like today you heard about this urbanization. I mean, the urbanization, the result, I don't know if it's true or not, but the same thing happening in India. It should be happening also in other cities in Asia or even the whole world. So there is one topic to be explored further. Philip, you want to say something?
Yes, maybe a remark and maybe a suggestion. Several people talking today have talked about a constellation of satellites for observing lightning. And actually, you probably know that a constellation of satellites for the communication, I mean, Starlink, for example, are a huge problem for radio astronomy and for astronomy in general. We detect them in our data as transient, and it's a really big problem. And so I wondered, of course, it's not the same number of satellites, but I wonder that as scientists, instead of planning a new constellation of satellites, if we could not explore the possibility to put scientific instrument on some of satellites of the communication constellations, like Starlink, OneWeb, or whatever. at least this would not increase the burden on astronomy of this, and maybe some of them could be useful, and it would solve the question of sending more regularly, because they need that for communication. So I wonder if at some level we could organize just to talk to these people.
Well, Philip, you have to organize a session proposal, to talk about that.
Yeah, sure.
I think there's a good topic indeed. I mean, how to add miniaturized instrument, right? Piggyback, so to say, on this kind of.
Exactly.
Yeah, I mean that I kind of think about in that direction too. But I think that it's very good that you mentioned this. So I will write to you. I think that's something that people really should concentrate on too. Yeah. So other gentlemen, ladies and gentlemen, you have any comment to add to, or you want to make a proposal also? I have the early bird who gave talks earlier. Gail, you want to say something, Professor Fischer?
Well, what I just wanted to say was, we also heard a lot about Venus light.
I can hear you.
Can you hear me?
Yeah, now, yeah, it's here, yeah.
Yeah, we also talked a lot about Venus lightning, and in fact, I think many people, and I also know of the late David Sandman, have now probably tried to detect Venus lightning with ground-based optical telescopes. But so far, nothing of this has been published. And I want to urge the people, even if there is no detection, even if it's a negative result, it should be published. Because until today, I mean, we still cite this 30-year-old paper of Hansel et al. 1995, which, in my opinion, if you compare how digital cameras were 30 years ago and how they are today, there is really, I mean, a giant leap for this. So for me, basically, I think that this Hansel detection he detected, I don't think he detected 7 optical lightning flashes, but he detected seven pixel errors. Yeah. So basically, because until today, several people have tried to observe this, but no one has published anything. Negative results don't get published. I mean, I published 3 papers about the non-detection of Titan lightning, and I urge people that observe Venus lightning to publish negative results. That's what I wanted to say.
Okay, that's an interesting thought. Usually we don't publish negative results.
Yes, that's true, but I published 3 papers about non-detection of Titan lightning, and why not?
Okay, good. Yeah, so we note that down, and then maybe we would send us a very short note about our discussion at this end. Okay. And I mean, is that all? I mean, there's other people too, if you don't mind, turn on your camera. And all right, let's smile then. Thank you. Thank you. Bye-bye. Bye. See you next time. Maybe in Japan.
Maybe in Japan. Yes. Bye-bye.
Okay.
Bye.
All right.